You are listening to the Developer's Linux Playbook. Like and subscribe to keep up to date on our latest audiobooks. The Developer's Linux Playbook. One welcome to Linux, why developers need it. For anyone embarking on, or advancing within, the world of software development, the operating system you choose is more than just a backdrop. It's a foundational tool that can profoundly impact your productivity, workflow, and even your understanding of computing itself. While Windows and macOS certainly have their merits, a distinct and powerful contender has consistently emerged as the system of choice for serious developers: Linux. This chapter sets the stage, introducing you to the philosophical underpinnings of Linux and unraveling the compelling reasons why it has become the operating system that powers much of the digital world, from personal devices to the global internet infrastructure. By the end of this journey, you'll understand why embracing Linux is not just a choice, but often a significant advantage for any developer. 1.1 What is Linux? A brief history and philosophy. Before diving into its developer-centric benefits, let's clarify what Linux is and where it came from. The term Linux is often used broadly, but strictly speaking, it refers to the Linux kernel. A kernel is the core of an operating system. It manages the computer's hardware and software resources, acting as a bridge between your applications and the physical components of your machine. The story of the Linux kernel begins in 1991, when a Finnish computer science student named Linus Torvalds started a personal project. He was dissatisfied with the licensing of Minix, a Unix-like operating system in use at the time, and decided to build his own. On August 25, 1991, he famously posted to a Usenet newsgroup, "I'm doing a free operating system, just a hobby, won't be big and professional like new, for 486 AT clones. It probably never will support anything other than at hard disks, and that's fine. Its file system is Minix, at least for now. It has no multitasking a la Minix, for example." Little did he know, this hobby would evolve into one of the most significant open-source projects in history. Linus released his kernel under a permissive license, allowing anyone to use, modify, and distribute it freely. This philosophy aligned perfectly with the ongoing GNU project, initiated by Richard Stallman in 1983. The GNU project aimed to create a complete, free, Unix-like operating system. While the GNU project had developed many essential tools, like the command-line shell bash, the GCC compiler, and utilities like ls and cat, it lacked a kernel. The Linux kernel filled this void, combining with GNU tools to form a complete, usable operating system, which is often referred to as GNU Linux, though Linux remains the common simplified term. This collaborative, open-source model is the very foundation of Linux. Unlike proprietary operating systems, where the source code is hidden and controlled by one company, Linux's code is open for anyone to inspect, improve, and adapt. This fosters a vibrant global community of developers, leading to rapid innovation, robust security through constant scrutiny, and unparalleled flexibility. 1.2 Why Linux for developers? Now, let's explore the concrete advantages Linux offers to software developers. These aren't just theoretical benefits. They translate directly into a more efficient, powerful, and enjoyable development experience. Stability and reliability. Linux systems are renowned for their stability. Designed with robust multi-user and multitasking capabilities inherited from its Unix lineage, Linux provides a solid foundation for demanding development tasks. It's common for Linux servers to run for months or even years without needing a reboot. This translates to fewer crashes, less downtime, and a more consistent work environment for developers. You can trust that your development tools and applications will run smoothly without unexpected interruptions. Flexibility and customization. One of Linux's greatest strengths is its incredible flexibility. Unlike operating systems that come with a fixed set of features and a prescribed user interface, Linux allows you to tailor almost every aspect of your environment. Want a minimalist system for embedded development, or a feature-rich desktop with multiple monitors for web development? Linux accommodates both. You can choose your desktop environment, GNOME, KDE, XFCE, etc., configure your command line shell, pick your default applications, and even compile your own kernel modules. This level of customization means you can optimize your development rig precisely to your needs, getting rid of bloat and focusing on what matters most to your workflow. The power of the command line interface, CLI. While Windows and macOS offer powerful graphical user interfaces, GUIs, Linux truly shines from the command line. The CLI is not just an alternative way to interact. It's the primary interface for many powerful development tasks and server management. With a few keystrokes, you can navigate complex file structures, manipulate large sets of data, install software, run scripts, and automate repetitive tasks. Many developers find that once they become proficient with the Linux CLI, their productivity skyrockets. It's a skill that pays dividends across various aspects of software engineering, from writing build scripts to deploying applications to servers. A rich development ecosystem. Linux provides a native and often optimized environment for nearly every programming language and development tool imaginable. Native language support. Whether you're working with Python, Node.js, Ruby, Go, C++, Java, Rust, or any other popular language, Linux offers first-class support. Compilers, interpreters, and runtime environments are readily available and often pre-installed or easily added through package managers. Vast tooling. A staggering array of open-source development tools, libraries, frameworks, and databases are developed on and for Linux. Need a web server? Apache and Nginx are Linux stalwarts. A database. PostgreSQL, MySQL, MongoDB, Redis, and more thrive on Linux. Build tools, version control systems, like Git, network utilities. Linux has them all, often with superior performance and integration. Containerization. The rise of container technologies like Docker and Kubernetes has revolutionized software deployment. These technologies heavily rely on Linux kernel features, like namespaces and cgroups, to create isolated, portable environments. Developing on Linux means your development environment is inherently closer to your production environment, reducing the "it worked on my machine" problem. Major tech companies like Google, Facebook, and Amazon have built immense, distributed infrastructures atop Linux, leveraging these very capabilities for scale and reliability. Security. Linux's open-source nature contributes to its robust security. With millions of eyes on the code, vulnerabilities are often identified and patched quickly. Its strong multi-user model and permission system, inherited from Unix, provide inherent layers of security by restricting access and privileges by default. While no system is perfectly secure, Linux's design principles and community-driven development make it a very secure platform for development and deployment. Furthermore, Linux tends to be less of a target for common malware compared to more widely used consumer operating systems. Cost and community. Most Linux distributions are completely free to download, use, and distribute. This eliminates licensing costs for your operating system, freeing up resources for other development tools or hardware. This open-source ethos extends to the community. When you encounter a problem or need help, you're not reliant on a single company's support channel. An enormous, active global community of users and developers provides online forums, documentation, tutorials, and instant help. Stuck on a problem at 2 in the morning? Chances are someone else has faced it and documented the solution online. 1.3 Linux distributions. Finding your flavor. Given Linux's flexibility, it's not surprising that there isn't just one Linux. Instead, there are many distributions, or distros, complete operating systems built on the Linux kernel, packaged with a specific set of GNU tools, applications, desktop environments, and configuration choices. Choosing the right distribution can be overwhelming for newcomers, but for developers, a few key families stand out. The Debian/Ubuntu family. Debian, known for its stability and strong commitment to free software. It's a foundational distribution, often chosen for servers due to its reliability. Ubuntu, perhaps the most popular desktop Linux distribution, Ubuntu is based on Debian but aims for user-friendliness and a modern desktop experience. It has a vast community, excellent documentation, and extensive software repositories. For many new Linux users and most developers, Ubuntu, or one of its derivatives like Linux Mint, which offers a more traditional desktop feel, is an excellent starting point due to its balance of simplicity and power. The Red Hat Fedora family. Fedora. Sponsored by Red Hat, Fedora is known for being on the cutting edge, incorporating the latest software innovations. It's a great choice for developers who want access to the newest packages and features, as it often serves as a testing ground for technologies that eventually make their way into Red Hat Enterprise Linux, RHEL, a major enterprise-grade server OS. CentOS RHEL. Red Hat Enterprise Linux and its community-supported rebuilds like CentOS or the newer CentOS Stream are primarily used in enterprise server environments. While not a common desktop choice for beginners, understanding these distributions is crucial if you plan to deploy your applications to professional servers. The Arch Linux family, Arch Linux. For developers who desire ultimate control and a deep understanding of their system, Arch Linux offers a do-it-yourself approach. It's a rolling release distribution, meaning you get continuous updates rather than distinct version upgrades, and provides a minimal base system, allowing you to build your environment from the ground up. This high level of customization comes with a steeper learning curve, but it's incredibly rewarding for those who embrace it. Manjaro is a popular, more user-friendly derivative of Arch. For most developers just starting with Linux, an Ubuntu-based distribution is often recommended due to its large community, ease of use, and extensive software availability, allowing you to focus more on coding and less on system administration in the beginning. 1.4 Linux versus other operating systems. A brief comparison. While this book focuses on Linux, it's helpful to understand its place in the operating system landscape for developers. Windows. Microsoft Windows is ubiquitous in the consumer market, and many developers use it. Its strength lies in its extensive software compatibility, particularly for proprietary tools and games. However, its command line environment and package management historically lagged behind Linux. The introduction of the Windows subsystem for Linux, WSL, has significantly improved the developer experience on Windows by allowing native Linux environments to run seamlessly. For developers, this often forms a hybrid environment. macOS. Apple's macOS is built on a Unix-like foundation, providing a robust command line experience similar to Linux. Many developers appreciate its elegant user interface and integration with Apple's hardware and ecosystem. However, macOS is proprietary, limited to Apple hardware, and less customizable than Linux. While it shares many command line tools with Linux, differences in file paths, package managers, and system services exist. Linux stands out for its open-source philosophy, unparalleled flexibility, and its strong presence in server infrastructures and cutting-edge development paradigms like containerization. It's the native environment where much of the digital world's plumbing is built and maintained. 1.5 Getting ready for the journey. Learning Linux for development is an investment that will pay dividends throughout your career. It might seem daunting at first, especially if you're accustomed to a purely graphical interface. But think of the command line as a new, incredibly powerful language you're learning to speak to your computer. This book will guide you through this journey step by step. We'll start with how to get Linux running on your machine, then move into mastering the command line, understanding the file system, and installing software. We'll then explore essential developer tools, shell scripting for automation, and how to set up robust development environments using technologies like Docker. Finally, we'll cover best practices for maintenance, security, and point you towards advanced topics. You don't need prior Linux experience to succeed with this book, just an eagerness to learn and a willingness to occasionally try things out in the terminal. Embrace the challenge, enjoy the power and freedom that Linux offers, and get ready to unlock your full development potential. Let's begin. Getting started. Installation and first steps. You've learned why Linux is a powerful and valuable asset for developers. Now, it's time to get your hands dirty and install it. This chapter will walk you through the various ways to set up a Linux environment, helping you choose the best method for your current needs. We'll then proceed with a step-by-step installation process, focusing on a popular and developer-friendly distribution, Ubuntu, installed within a virtual machine. This approach provides a safe, low-risk environment for your first foray into Linux. Finally, we'll cover the essential post-installation tasks to get your new system ready for development. 2.1 Choosing your Linux experience. Installation methods. There are several ways to get a Linux system up and running. Each method has its pros and cons, making certain approaches more suitable for different scenarios. Virtual machine, VM. A virtual machine allows you to run a complete operating system, like Linux, as a program within your existing operating system, like Windows or macOS. The VM creates a simulated computer that Linux runs inside, completely isolated from your host system. Benefits. Safety. Your current operating system and data are completely protected. Experiments, mistakes, or even system crashes within the VM won't affect your host machine. Reversibility. VMS can be easily deleted, reverted to a previous snapshot, or copied. Flexibility. You can run multiple VMS, each with a different Linux distribution or a different configuration, without needing separate hardware. Portability. VM images can often be moved between different physical machines. Drawbacks. Performance overhead. Running a guest OS on top of a host OS can introduce a slight performance penalty, though modern virtualization software and hardware minimize this for most development tasks. Resource consumption. The VM will consume RAM, CPU, and disk space from your host machine. Use cases. Ideal for experimentation, learning Linux without committing to a full installation, testing software across different Linux versions, or for development environments that need to be easily replicated or contained. This is the recommended method for your first Linux installation. Popular tools: VirtualBox, free, open source, cross-platform, VMware Workstation Player, free for personal use, KVM Linux Native Hypervisor, Windows Subsystem for Linux, WSL. WSL allows you to run a full-fledged Linux environment directly within Windows, without the overhead of a traditional virtual machine. It essentially provides a compatibility layer that translates Linux system calls into Windows system calls. Benefits: seamless integration, high performance, native file system access. You can access your Windows files directly from Linux. Low overhead, much lighter than a traditional VM. Convenience: easily install multiple Linux distributions from the Microsoft Store. Drawbacks: not a full Linux system. While WSL2, the latest version, runs a real Linux kernel in a lightweight utility VM, it's not a complete standalone Linux installation. It might have limitations for certain hardware-intensive tasks or graphical applications. Windows dependency. You're still relying on Windows as your primary operating system. Use cases. Excellent for Windows developers who need a quick and performant Linux command line environment for development tools, scripting, or running server-side applications without leaving their familiar Windows desktop. Dual boot. Dual booting involves installing Linux alongside your existing operating system, e.g., Windows, on the same physical hard drive. When you start your computer, you'll be given a choice of which operating system to boot into. Benefits: native performance. Linux runs directly on your hardware, providing the best possible performance as there's no virtualization layer. Full hardware access. All your computer's resources are dedicated to Linux. Drawbacks: partitioning risk. Requires repartitioning your hard drive, which carries a small risk of data loss if not done carefully. Switching requires reboot. To switch between Linux and your other OS, you must restart your computer. Bootloader management involves configuring a bootloader, like Grub, to manage which OS starts. Use cases. For developers who want Linux as their primary operating system for desktop use while retaining the option to use another OS, or for performance-intensive tasks that benefit from direct hardware access. Replacing current OS, full installation. This method involves completely wiping your hard drive and installing Linux as your sole operating system. Benefits: pure Linux experience, total dedication to the Linux ecosystem, maximum control, no other OS conflicts or resource sharing. Drawbacks: data loss, all existing data on your hard drive will be erased. No fallback. If you need features or software exclusive to another OS, you're out of luck. Use cases: ideal for those who are fully committed to using Linux, perhaps on an older machine, or building a dedicated Linux development workstation. Cloud instances. Many cloud providers, like Amazon Web Services, Google Cloud Platform, Microsoft Azure, DigitalOcean, Linode, offer virtual servers that primarily run Linux. Benefits: scalability, easily scale resources up or down. Accessibility, accessible from anywhere with an internet connection. Production environment, often reflects your production environment, useful for testing deployments. Drawbacks. Cost, while small instances can be free or very cheap, costs can add up. Network dependency, requires an internet connection for access. Use cases, primarily for hosting applications, testing deployments, setting up remote development environments, or backend server development. Less common for local desktop development. For the purpose of your first hands-on experience and to ensure a safe learning environment, we will focus on installing Ubuntu Desktop within a virtual machine. 2.2 Essential pre-installation steps. Regardless of which installation method you choose, a few preparatory steps are crucial. Back up your data. This is paramount, especially if you're considering dual booting or a full installation. Even for a VM, it's good practice to ensure your important files on the host machine are backed up. Download the Linux distribution ISO. You'll need the installation file, typically an ISO image. For this guide, we'll use Ubuntu Desktop. Visit ubuntu.com/download/desktop and download the latest long-term support (LTS) version. LTS releases are supported for several years and offer a stable foundation. Choose and install virtualization software. For this book, we recommend VirtualBox due to its widespread use, cross-platform compatibility, and ample features for a free product. Download it from virtualbox.org/wiki/downloads. Install it on your Windows or Mac OS machine like any other application. Check system requirements. While most modern computers can run a Linux VM, ensure your system meets the minimum requirements for both VirtualBox and Ubuntu, e.g., sufficient RAM, CPU cores, and disk space for the VM. 2.3 Step-by-step installation. Focus on Ubuntu Desktop in VirtualBox. Let's walk through installing Ubuntu Desktop in a VirtualBox environment. 2.3.1 Setting up a virtual machine in VirtualBox. Open VirtualBox. Launch the VirtualBox application. Create a new virtual machine. Click the New button or Machine New in the menu. Name an operating system. Name. Give your VM a descriptive name, e.g., Ubuntu Dev. Machine folder. Choose where the VM files will be stored. ISO image. Click the drop-down and navigate to Other to select the Ubuntu ISO file you downloaded. Type Linux. Version Ubuntu 64-bit. Click Next. Hardware base memory. Allocate RAM to your VM. A good starting point is 4096 MB, 4 GB, or more if your host machine has plenty to spare. Avoid allocating more than half of your host's RAM. Processors. Allocate CPU cores. 2 or 4 is generally suitable for development. Click Next. Virtual hard disk. Disk size. Allocate space for your VMS hard drive. 25 GB is the minimum recommended for Ubuntu, but 40 to 60 GB or more is better for development, as you'll install tools and store project files. Select Create a virtual hard disk now. File type, keep the default VDI if creating from scratch. Storage on physical hard disk. Select Dynamically Allocated. This means the disk file will only grow as you use space inside the VM, up to the maximum size you set. Click Next if prompted, then Finish. Your new VM will appear in the VirtualBox Manager on the left panel. 2.3.2 The Ubuntu installation process. Start the VM. Select your new Ubuntu Dev VM in the VirtualBox Manager and click the Start button. Initial boot. The VM will boot from the Ubuntu ISO. You might see a prompt to try or install Ubuntu. Choose Try or Install Ubuntu and press Enter. Live Environment and Installation Wizard. Ubuntu will boot into a live environment, allowing you to try it without installing. On the desktop, you'll see an Install Ubuntu 2 X-Roman 20X LTS icon. Double-click it to start the installation wizard. Welcome, choose your language, then click Continue. Keyboard layout. Select your keyboard layout, then click Continue. Updates and other software. Choose Normal installation. Check Download updates while installing Ubuntu, requires internet connection. Check install third-party software for graphics and Wi-Fi hardware and additional media formats. This is generally recommended. Click Continue. Installation type, crucial step. Because you are installing inside a VM, select Erase Disk and install Ubuntu. VirtualBox provides an isolated virtual disk, so this will only affect the VMS disk, not your host machine's actual hard drive. Click Install Now. Confirm the changes to the disk by clicking Continue on the warning prompt. Where are you? Click on your location on the map to set your time zone. Click Continue. Who are you? Your name. Enter your full name. Your computer's name. This will be your host name, e.g., your name VirtualBox. Pick a username. This is your login username. Choose a password. Crucially, choose a strong password. Memorize it as you'll need it frequently. Select Require my password to log in for security. Click Continue. Installation progress. The installer will now copy files and configure your system. This may take some time depending on your computer's speed. Installation complete. Once finished, you'll be prompted to restart now. Remove the virtual installation disk. VirtualBox will usually prompt you to press Enter after unmounting it and press Enter. First login. Your VM will reboot. At the login screen, click on your username and enter the password you created. Congratulations! You've successfully installed Ubuntu Desktop in a virtual machine. 2.4 Post-installation essentials. After your first successful login, there are a few immediate steps to ensure your Linux system is ready for development. 2.4.1 Run system updates. Keeping your system updated is vital for security, stability, and access to the latest features. Linux relies on package managers to handle software installation and updates. Ubuntu uses apt Advanced Package Tool. Open the terminal. This is your primary interface for interacting with Linux from the command line. In Ubuntu, you can typically find it in your Applications menu or press Ctrl plus Alt plus T. Refresh package lists, sudo apt update. You will be prompted for your user password. Sudo stands for superuserdo and allows you to execute commands with administrative privileges. Apt update downloads the latest package information from Ubuntu's software repositories. Upgrade installed packages, sudo apt upgrade. This command downloads and installs updated versions of all installed packages on your system. It will often ask you to confirm by typing Y and pressing Enter. 2.4.2 Install Build Essentials. For developers, one of the first things you'll need is a set of tools for compiling software, often referred to as Build Essential. This package includes common compilers like GCC for C, C++, Make, and other utilities frequently used in software development. Sudo apt install build essential. 2.4.3 Install common development utilities. If not already present, some widely used utilities might not be installed by default or come with older versions. It's good practice to ensure you have them. Git, essential for version control. Curl, a command line tool for transferring data with URLs. wget, another command line utility for downloading files from the web. Sudo apt install git curl wget. These commands will check if the packages are installed, and if not, download and install them along with any necessary dependencies. 2.5 First interactions. The terminal. You've already used the terminal to run updates. Let's try a few very basic commands to get a feel for it. pwd, print working directory. This command tells you your current location in the file system. pwd. You'll likely see home/your username, which is your home directory. ls list. This command lists the contents of the current directory. ls. You'll see familiar directories like desktop, documents, downloads, etc. Whoami. This command displays your current username. Whoami. It will show the username you created during installation. Notice the prompt in your terminal. It usually looks something like your username at your computer name, $. Your username is the currently logged in user. Your computer name is the host name of your machine, the name you gave it during installation. Separates the username and host name from the current directory. Is a shortcut for your home directory, /home/your username. This indicates you are currently in your home directory. Indicates that you are a regular user. If it were, you'd be the root user. These first steps might seem small. but you've successfully created your own Linux development environment and taken your first steps into the powerful world of the command line. In the next chapter, we'll dive much deeper into navigating the Linux file system and mastering essential command line tools. 3. Navigating the command line, your development hub. In the previous chapter, you successfully installed Linux and performed some initial setup tasks using the terminal. Now it's time to truly embrace the command line interface, CLI. For developers, the CLI is not just an optional feature. It's a fundamental, powerful hub for virtually every aspect of software development. It might seem intimidating at first, especially if you're used to clicking buttons and dragging icons, but mastering the CLI will supercharge your productivity, automate tedious tasks, and open up a world of possibilities for remote work and server management. This chapter will demystify the CLI, teaching you how to confidently navigate the Linux file system, manipulate files, and effectively use powerful command line tools that are indispensable for any developer. 3.1 The Power of the Prompt. Why the CLI? Why do developers spend so much time typing commands into a black and white window when graphical interfaces exist? The short answer is efficiency, power, and automation. Speed and efficiency. Once you know the commands, interacting with your system from the CLI is often much faster than clicking through menus and windows. You can perform complex operations with a single line of text. Automation. The true magic of the CLI lies in its ability to be scripted. You can combine multiple commands into powerful scripts to automate repetitive tasks, build software, deploy applications, and manage server environments without manual intervention. This is a core skill for DevOps and system administration. Remote access. When you work with servers in the cloud, which are almost exclusively Linux-based, you access them primarily through the CLI using tools like SSH, Secure Shell. Your local CLI skills translate directly to managing remote machines. Resource-friendly. CLIs consume fewer system resources, CPU, RAM, than graphical applications, making them ideal for lightweight development environments, older hardware, and servers where every byte of memory counts. Universal language. The core commands and concepts of the Linux CLI are remarkably consistent across different Linux distributions and even other Unix-like systems, like macOS. Once you learn them, you can apply your knowledge broadly. 3.2 Anatomy of a command. Every command you type into the terminal follows a general structure. Command options /flags, arguments. Let's break this down. Command. This is the executable program you want to run. Examples include ls, cd, grep, mkdir, etc. Options or flag switches. These modify the behavior of the command. They usually start with 1 hyphen for a short, single-letter option or 2 hyphens for a longer, more descriptive option. Example, lsll is an option to list in long format. Example, lsall is an option to show hidden files. Multiple short options can often be combined. lsla same as lsla. Arguments. These are the inputs the command acts upon, such as file names, directory paths, or strings of text. Example, cp myfiletxt home user documents. Myfiletxt and home user documents are arguments. The sudo command. You've already encountered sudo. It stands for superuserdo, and it allows you to execute a command with administrative root privileges. This is crucial for tasks like installing system-wide software or modifying protected system files. Important: use sudo with caution. It grants immense power, and an incorrectly used sudo command can damage your system. Always double-check commands that begin with sudo before pressing enter. When you use sudo for the first time in a session, you'll be prompted for your user password, not the root password. 3.3 Essential navigation commands. Your computer's file system is organized like a tree, starting from the root directory. Understanding how to move around this tree is fundamental. pwd, print working directory, shows your current location, the directory you are currently in. pwd. Hash expected output, home/username. lslist lists the contents of the current directory. ls. Hash expected output, desktop documents downloads public, useful options for ls, lsl. Lists in long format, providing detailed information like permissions, owner, file size, and modification date. LSA shows all files including hidden ones, those starting with a dot like bashrc. LSH, used with L e.g. LSLH to show file sizes in human-readable format e.g. 4.0K, 1.2M, 1.7G. LSF appends a character to entries to indicate file type, e.g. / for directories, for executables. CD change directory, used to move between directories. Absolute paths start from the root. CD /local/bin. PWD hash expected output /local/bin. Relative paths start from your current directory to move into a subdirectory. CD documents. PWD hash expected output home/username/documents. To move up one directory refers to the parent directory. CD PWD hash expected output home/username. To move to your home directory is a shortcut for your home directory /home/username. CD PWD hash expected output home/username. You can also just type CD without an argument to go to your home directory. To go back to the previous directory you were in, CD mkdir make directory creates a new directory. mkdir minoproject. LS hash expected output will now include minoproject. You can create nested directories with the P option. mkdir p parent child grandchild. rmdir remove directory deletes an empty directory. rmdir empty folder. If the directory is not empty, rmdir will fail. For non-empty directories, you'll need the rm command discussed next. 3.4 File manipulation. Create, copy, move, delete. Once you can navigate, you'll want to manage files. Touch creates a new, empty file or updates the modification timestamp of an existing file. Touch to do txt. ls. cp copy copies files and directories. Copy a file. cp to do txt to backup txt. ls. Hash you'll now see both files. Copy a file to another directory. cp to do txt ~documents/. Hash to do txt is copied to your documents folder. Copy a directory recursively, r or recursive. cp r minoproject copy. mv move/rename moves files or directories and also renames them. Rename a file. mv to do txt tasks.txt. ls. Hash to do txt is now tasks.txt. Move a file to another directory. mv tasks.txt ~documents/. Hash tasks.txt moves to your documents folder from current location. rm remove deletes files and directories. Delete a file. rm tasks.txt delete an empty directory, just like rmdir. rmdir empty folder hash if it contains files, this fails. Delete a non-empty directory, recursively rm r minoproject copy. Delete with force F. This skips confirmation prompts and is very dangerous. Use with extreme caution. rmf important file txt hash deletes without asking. The most dangerous command. rmref or rmref asterisk. rmref. This command, if run as root, would recursively delete everything from the root of your file system. It would effectively wipe your entire operating system. Never run this. rmref. This command, if run in a directory, would recursively delete everything in that directory. Always be careful with rm, r, and f. There is no undo in the command line. Many developers have stories of accidentally deleting important files early in their Linux careers. It serves as a permanent lesson in caution. 3.5 Viewing and searching content. Now that you can navigate and manage files, let's look at how to inspect their contents and find specific information. Cat concatenate displays the entire content of a file to the terminal, best for small files. Cat etc. os release. Hash this shows info about your Ubuntu version. Less/more. Used to view large files page by page. Less is generally preferred over more because it allows you to scroll both forwards and backwards. Less var/log/syslog. Inside less, spacebar or F. Scroll forward a page. B. Scroll backward a page. Your search term, search for text, press N for next match. Q. Quit. Head/tail, head file name, displays the first 10 lines of a file. Tail file name displays the last 10 lines of a file. You can specify the number of lines. Head N20 file name for the first 20 lines. Tail F file name. This is incredibly useful for watching log files in real time. It follows the file, displaying new lines as they are appended. Press Ctrl+C to stop. Tail F var/log/authlog. grep global regular expression print. A powerful tool for searching text patterns within files or command output. Grep error /var/log/syslog hash finds lines containing error in the syslog. Common grep options. Grep I pattern, case-insensitive search. Grep R pattern path/to/dir, recursively search for pattern in files within a directory and its subdirectories. Grep N pattern, show line numbers of matches. Find, locates files and directories based on various criteria, name, size, type, modification time, etc. Find, name txt, hash finds all text files in the current directory and its subdirectories. Find home/your/username type f, size +1g hash, finds files larger than 1 GB in your home directory. In find, name refers to the current directory. 3.6 Getting help, man pages and help. You don't need to memorize every command and option. Linux has built-in documentation. Manual pages. Provides comprehensive documentation for most commands. Man ls. Inside a man page, you can use the same navigation keys as less, spacebar to scroll down, B to scroll up, to search, Q to quit. Man pages typically have sections like name, synopsis, how to use the command, description, options, examples, and see also. Help or H. Many commands offer a brief help summary by appending help or H to the command. This is often quicker than man for quick reminders. Grep help. 3.7 Input, output, and redirection. A crucial concept in the CLI is how commands interact with data. Commands typically have 3 standard streams. Standard input, stdin, represented by 0, where a command gets its input from usually the keyboard. Standard output, stdout, represented by 1, where a command sends its normal output, usually the terminal screen. Standard error, stdir, represented by 2, where a command sends error messages, also usually the terminal screen. You can manipulate these streams using redirection and pipes. Pipes. The pipe symbol takes the stdout of one command and sends it as stdin to another command. This allows you to chain commands together to perform powerful operations. LSL less hashlist files in long format, then pipe the output to less for paginated viewing. LL grep miproject hash. LL is an alias for LSL list files, then filter for lines containing miproject. Find, name log zargs grep error hash find all log files, then search for error in each. Zargs executes a command for each item. Redirection. You can redirect output to a file instead of the screen, or input from a file instead of the keyboard. Redirect stdout overwrites, sends the stdout of a command to a file. If the file exists, its contents are overwritten. LSL fileless.txt hash saves the list of files to fileless.txt. Redirect stdout appends, sends the stdout of a command to a file. If the file exists, the output is appended to the end. Echo, this is a new line. Fileless.txt hash adds, this is a new line, to fileless.txt. Redirect stdin, uses the content of a file as stdin for a command. Sort unsorted names.txt hash sorts the lines in unsorted names.txt. Redirecting stdir, command to error output.txt. Redirects only standard error to a file. Command alloutput.txt 2 and 1 redirects both standard output and standard error to the same file. The 2 and 1 means redirect channel 2, stdir, to the same place as channel 1, stdout. Command and alloutput.txt, a shorthand for redirecting both stdout and stdir to a file, works in Bash and some other shells. 3.8 Command history and tab completion. These two features will dramatically speed up your command line work. Command history, your terminal remembers commands you've typed. Up and down arrow keys. Press the up arrow key to cycle through previous commands, down to cycle towards more recent ones. History command displays a numbered list of recently executed commands. Reverse iSearch, Ctrl+R. Press Ctrl+R and start typing part of a command you remember. Bash will search your history and show you the most recent match. Keep pressing Ctrl+R to cycle through older matches. Press Enter to execute the command or the right arrow key to edit it. Tab completion. This is arguably the biggest time saver on the command line. Commands. Type the first few letters of a command and press Tab. If there's only one match, it completes it for you. Files and directories. Type the first few letters of a file name or directory name after a command or during navigation. CD, CP, MV, RM, and press Tab. It will complete the name. Multiple matches. If there are multiple possible completions, press Tab twice to display all options. Example, if you have directories miproject alpha and miproject beta. CD mip tab, nothing happens if both start with mip. CD mip tab shows miproject alpha / and miproject beta /. CD miprojecta tab completes to CD miproject alpha /. With these fundamental commands and concepts, you now possess the core skills to navigate, inspect, and manipulate your Linux file system. The command line is a developer's best friend. It's powerful, efficient, and endlessly customizable. Practice these commands regularly, and you'll soon find yourself thinking in terms of commands rather than clicks. In the next chapter, we'll delve deeper into the Linux file system structure and explore how permissions protect your files and data. 4. Understanding the Linux file system and permissions. You've mastered the basics of navigating and manipulating files and directories from the command line. Now it's time to delve deeper into the structure and principles that govern the Linux file system. Unlike Windows, which typically uses drive letters C, D, or macOS, which presents a unified graphical view, Linux follows a specific hierarchical structure. Understanding this structure and the critical concept of file permissions is essential for every developer working on Linux. It impacts where you install software, store your projects, and how you manage access to files within collaborative environments. 4.1 The Linux File System Hierarchy Standard, FHS. The Linux file system adheres to the File System Hierarchy Standard, FHS, a consistent structure that defines the purpose of various directories. This consistency is a major strength of Linux, as it means you'll always find certain types of files in expected locations, regardless of the specific distribution you're using. Let's explore some of the most important top-level directories you'll encounter. /root directory. This is the ultimate parent directory for all other directories and files on the system. Everything begins here. /bin binaries. Contains essential command line utilities that are available to all users, such as ls, cp, mv, rm, cat, etc. These are fundamental commands needed for the system to function. sbin, system binaries. Similar to bin, but contains essential system administration binaries that are typically used by the root user or system processes, like iptables for firewall, fdisk for disk partitioning or reboot, etc., etc. This directory stores system-wide configuration files. Examples include network settings, user management files, password, shadow, and application configuration, Apache 2.conf, nginx.conf. As a developer, you'll often interact with configuration files here. Home, user home directories. This is where individual users' personal files and configuration settings are stored. Each user on the system has their own subdirectory, e.g., home/your username. This is where you'll generally find your documents, downloads, and project folders. The tilde symbol is a shortcut for your current user's home directory. /usr, Unix system resources, contains user programs and data that are not essential for the system to boot or run single-user mode. It's one of the largest directories and houses a significant portion of the installed software. usr/bin, most user executable programs are stored here, e.g., Python, Node.js, Git binaries. usr/lib, libraries used by programs in /usr/bin. usr/local, designed for programs and data that are installed locally by the system administrator, not part of the standard distribution. Many developers compile and install personal tools or newer versions of software here. var, variable data, contains variable data that changes frequently during system operation. var/log, system log files, e.g., syslog, authlog, crucial for debugging and troubleshooting. /var/www, often the default location for web server content if Apache or Nginx are installed. var/lib, state information for programs, e.g., databases. Opt, optional add-on applications, used for installing large, self-contained software packages from third-party vendors. For example, some proprietary software or large development environments, like certain IDEs, might install here. /tmp, temporary files, stores temporary files created by applications and users. The contents of this directory are typically cleared upon system reboot. Do not store anything important here. /dev, devices, contains special files that represent hardware devices, e.g., /dev/SDA for the first hard drive, /dev/null for a black hole device that discards all data written to it. Proc, process information, a virtual file system that provides information about running processes and kernel parameters. It's not stored on disk, but generated on the fly by the kernel. /mnt and media, used as temporary mount points for external storage devices, USB drives, network shares, CD/DVDs. /mnt is often used for manually mounted file systems, while media is typically for automatically mounted removable media. 4.2 Users and Groups. Linux is a multi-user operating system, designed from the ground up to handle multiple users working on the same system, either simultaneously or sequentially. This multi-tenancy is managed through users and groups. Users, each person or service that interacts with a Linux system, has a user account. Root, the superuser. This user has absolute administrative privileges and can do anything on the system. You only use sudo to temporarily gain root privileges for specific commands. It's a security best practice never to log in directly as root for everyday tasks. Regular users, like the user account you created during installation, your username. Regular users have limited privileges to prevent accidental system damage and enhance security. They typically have full control only over files within their own home directory. System users, accounts created by the system for specific services, e.g., Apache, Nginx, MySQL. These users typically cannot log in interactively and are used to run services with minimal necessary privileges. Groups. Users are organized into groups. Permissions can be assigned to a group, and all members of that group inherit those permissions. This simplifies managing access for multiple users. When you create a user, a group with the same name as your username is usually created by default, and you are the sole member. Users can be members of multiple groups. For instance, your user is likely part of the sudo group, which grants them the ability to use the sudo command. To see what groups your user belongs to, groups your username. #example output, your username. Your username Adam Cdrom sudo dip plugdev lpadmin sambashare. To see all users and groups on the system, by inspecting relevant configuration files. cat etc /password #lists users. Cat etc group #lists groups. 4.3 Understanding file permissions. The Linux permissions system dictates who can read, write, or execute a file or directory. This is fundamental to system security and multi-user environments. When you list files using LSL, the first column shows the permissions string. LSL myfile.txt mydirectory/. Example output. rwrr1 your username 123 jan 110 myfile.txt. drwxrxrx 2 your username 4096 jan 1110 mydirectory/. Let's break down that permission string, focusing on rwrr and drwxrxrx. The first character, this indicates the file type, a regular file. D, a directory. L, a symbolic link shortcut. Other characters denote special file types, e.g. B for block device, C for character device, P for named pipe, S for socket. The next 9 characters, permissions triples. These are broken into 3 sets of 3 characters, defining permissions for 3 categories of users. User owner. The first 3 characters, RW. These are the permissions for the user who owns the file. Group. The next 3 characters are. These are the permissions for the group that owns the file. Others, the last 3 characters are. These are the permissions for everyone else on the system. Within each set of 3, the characters have the following meaning. R. Read. For files, allows viewing the content of the file. For directories, allows listing the contents of the directory, but not entering it or viewing file details without X. W. Write. For files, allows modifying or deleting the file. For directories, allows creating, deleting, or renaming files within that directory. X. Execute. For files, allows running the file as a program or script. For directories, allows entering the directory and accessing its contents if R is also granted on the directory. Example deconstruction, myfile.txt rwrr, owner, your username, has read R and write W permissions, can view and modify the file. Group, your username, has read R permission, can view but not modify. Others has read R permission, can view but not modify. My directory /drwxrxrx, owner, your username, has read R, write W, and execute X permissions, can list, create, delete files in and enter the directory. Group, your username, has read R and execute X permissions, can list and enter the directory but not create, delete files. Others has read R and execute X permissions, can list and enter the directory but not create, delete files. 4.4 Changing permissions, ownership and group. You can modify file permissions and ownership using specific commands. chmod, change mode. Chmod changes file permissions. Permissions can be specified in two ways. Symbolic mode, easier for specific changes. Who, you user owner, G group, O others, A all. Operation, plus add permission, remove permission, equals set exact permissions. Permission. R, W, X examples. chmod u plus X miscript sh, hash add execute permission for the owner. chmod go W myfile.txt, hash remove write permission for group and others. chmod a equals rw myDataJSON hash, set read and write permissions for all. Remove execute. Octal numeric, mode more common for setting complete permission sets. Each permission RWX has a numeric value. R equals 4 read, W equals 2 write, X equals 1 execute, equals no permission. You sum these values for each triplet owner, group, others. Permission binary, octal. 00, X11, W102, WX113, R104, RX101 RW110 6, RWX111 7. A common permission set for files is 644, RWRR. Owner can read-write, group others can only read. A common permission set for directories is 755, RWXRXRX. Owner can read-write execute, group others can read-execute, allowing traversal. Examples. chmod 644, myDocument.txt hash, sets permissions to RWRR. chmod 755, miprojectdir hash, sets permissions to RWXRXRX. chmod 700 mipraveki hash, sets permissions to RWX. Only owner can read-write execute. You can apply chmod recursively to directories using the R option, e.g. chmod R 755 miprojectdir. Chown change owner. Chown changes the owner of a file or directory. You usually need sudo for this. Sudo chown newser file.txt, hash change owner of file.txt to newser. Sudo chown newser. Newgroup file.txt, hash change owner to newser and group to newgroup. Sudo chown r newser. Newgroup myup / hash recursively change owner and group for a directory and its contents. chgrp, change group. chgrp changes the group owner of a file or directory. You usually need sudo for this, unless you are changing to a group you are already a member of. Sudo chgrp developers project files.txt, hash change group of project files.txt to developers. 4.5 Practical applications of file system knowledge and permissions. Understanding the file system hierarchy and permissions is crucial for many developer tasks. Installing software. Knowing whether a script belongs in usr/local/bin for system-wide access or bin for your user only is important. Managing configuration. You'll often modify configuration files in etc., e.g., web server configs, SSH settings. Remember sudo is needed. Debugging. Checking log files in var/log is a daily activity for diagnosing issues. Web development. If you're hosting websites, your web server, e.g., Apache Nginx, typically runs as a specific user, e.g., www data. You'll need to ensure your web project files have the correct permissions, R for the web server user group, and directory execute permissions, X, so the server can read and serve them. Often, files are 644 and directories are 755. Security. Incorrect permissions can lead to security vulnerabilities. For instance, private keys should have 600 permissions, RW, so only the owner can read-write them. Misconfigured directories with 777, RWX mean anyone can read, write, or delete files, which is a significant security risk for anything other than temporary internet-facing directories that are explicitly designed for public write access. Case study: setting up a web project directory. Imagine you're deploying a simple web application to your Linux server. You decide to put your HTML and CSS files in /var/www/myapp. Create the directory, sudo mkdir/var/www/myapp. This creates the directory owned by root with 755 permissions by default. Copy your web files, sudo cpr //var/www/myapp/. The files are now owned by root. Your web server, running as user www data, needs to read these files. Adjust ownership and permissions. You want the web server user www data to be able to read the files, and you, as your username, to be able to manage them easily. Change group ownership to www data. Sudo chown r your username, www data/var/www/myapp. Now your username is the owner, and www data is the group owner. Set appropriate permissions. Sudo find /var/www/myapp type d exec chmod 755 / directories rwxrxrx. Sudo find /var/www/myapp type f exec chmod 644 / files rwrr. This ensures your username can read-write, and the www data group, and thus the web server, can read the files and traverse the directories. Understanding these concepts will make you a more capable and secure Linux developer. You'll intuitively know where files should go and how to grant the right level of access, avoiding common pitfalls. In the next chapter, we'll continue building on this foundation by exploring how to manage software efficiently using package managers. 5. Managing software. Package managers. You've learned how to navigate the file system and understand file permissions. Now that your Linux system is set up, you'll inevitably need to install new software, update existing programs, and remove applications you no longer need. This is where package managers come in. They are the unsung heroes of the Linux operating system, making software management incredibly efficient and reliable. For developers, a solid grasp of package managers is non-negotiable. You'll use them constantly to install programming language runtimes, development tools, libraries, and utilities. This chapter will introduce you to the concept of packages, explain why package managers are so vital, and guide you through using the apt package manager, which is prevalent in Ubuntu and Debian-based systems. 5.1 What are packages and why use a package manager? In Windows or macOS, installing software often involves downloading an installer executable, exe or DMG from a website, clicking through a wizard, and hoping all necessary dependencies are met. Uninstalling can be equally haphazard, sometimes leaving behind orphaned files. In Linux, software is distributed in packages. A package is a compressed archive containing the application's binaries, the executable programs, configuration files, documentation, information about its dependencies, other software or libraries that the application needs to run, instructions for installation and uninstallation. A package manager is a system or collection of tools that automates the process of installing, upgrading, configuring, and removing software packages. Here's why they are indispensable. Dependency resolution. This is perhaps the biggest advantage. Complex software often relies on many other pieces of software. A package manager automatically identifies and installs all necessary dependencies, ensuring the new application runs correctly. No more DLL hell or missing library errors. Centralized repositories. Packages are retrieved from official repositories, servers controlled by the distribution. This ensures that software is vetted, compatible with your system, and generally safe. Easy updates. Keeping your entire system updated is as simple as running a single command. The package manager checks for new versions of all installed software in the repositories. Clean uninstallation. When you remove a package, the package manager tracks all its components and dependencies, unless shared with other programs, and removes them cleanly, preventing system clutter. System consistency. By managing installations from a trusted source, package managers help maintain the integrity and stability of your system. 5.2 Common Linux Package Managers. While the core concept is similar, different Linux distribution families use different package management systems. apt Advanced Package Tool, used by Debian, Ubuntu, Linux Mint, and many other Debian-based distributions. This is what we will focus on. Commands usually start with apt. Historically, apt-get was the primary command, but apt has become the preferred user-facing command as it wraps apt-get and apt-cache functionalities with a more user-friendly interface. DNF, Dandified Yum. Used by Fedora, CentOS Stream, and Red Hat Enterprise Linux, RHEL, it is the successor to Yum. Pacman, used by Arch Linux and its derivatives like Manjaro, known for its speed and simplicity. Zypper, used by OpenSUSE and SUSE Linux Enterprise. For this book, given our focus on Ubuntu, we will concentrate on the apt commands. 5.3 Using apt for package management. You've already used apt in Chapter 2 to update your system and install Build Essential. Let's explore its commands in more detail. Important: most apt commands require sudo privileges because they modify system-wide software. 5.3.1 Updating package information. Before installing any new software, it's crucial to update your system's package index, a local database of available packages and their versions from the configured repositories. Sudo apt update. This command does not install or upgrade software. It only fetches the latest list of available packages. 5.3.2 Upgrading installed packages. Once your package index is updated, you can upgrade all installed packages to their latest available versions. Sudo apt upgrade. This command upgrades existing packages while resolving dependencies. It's generally safe as it avoids breaking changes, e.g., wouldn't remove an essential package to satisfy a dependency. It will prompt you to confirm the action. For a more aggressive upgrade that can remove existing packages to make room for new ones or to resolve complex dependency chains, you can use sudo apt full upgrade. Use this with caution, typically only for major distribution upgrades. 5.3.3 Installing new packages. To install a specific package or multiple packages, you use the install command. Sudo apt install package name. Example: install the Nginx web server. Sudo apt install Nginx. You can install multiple packages at once. Sudo apt install htopnet tools. The package manager will examine dependencies, tell you how much disk space will be used, and ask for confirmation. 5.3.4 Searching for packages. If you don't know the exact name of a package or want to explore available software, use the search command. Apt search keyword. Example: search for Python 3 development tools. Apt search Python 3 dev. This will return a list of package names and brief descriptions that match your keyword. 5.3.5 Viewing package information. Once you found a package, you might want more details before installing, such as its version, dependencies, or a longer description. Apt show package name. Example: apt show Nginx. 5.3.6 Removing packages. If you no longer need a package, you can remove it. Sudo apt remove package name. Example: sudo apt remove Nginx. This command removes the package binaries and documentation, but typically leaves configuration files behind. This can be useful if you plan to reinstall the package later, retaining your settings. To remove a package along with its configuration files, use purge. Sudo apt purge package name. Example, sudo apt purge nginx. This is useful for a clean removal, especially if you want to completely revert specific software settings. 5.3.7 Cleaning up unused dependencies. Over time, as you install and remove software, some packages that were installed as dependencies might no longer be needed by any other active software. You can remove these orphan packages to free up disk space. Sudo apt auto remove. It's a good practice to run this command occasionally. 5.4 Beyond apt. Software sources and PPAs. While apt primarily downloads packages from your distribution's official repositories, sometimes you might need newer software versions or packages not available there. This often leads to using personal package archives, PPAs, or directly adding third-party repositories. PPAs are repositories hosted on Launchpad, allowing developers to make packages available directly to Ubuntu and its derivatives. Adding a PPA. Sudo adapt repository PPA, some /developer/PPA name. After adding a PPA, you must run sudo apt update again to fetch the new package lists from the added repository. Removing a PPA. Sudo adapt repository remove PPA, some /developer/PPA name. Again, sudo apt update is required after removal. Caveat: while PPAs can be convenient, exercise caution. Only add PPAs from trusted sources, as they can sometimes contain unstable or malicious software or conflict with official packages. For production systems, it's often better to stick to official repositories or use containerization, which we'll discuss later, for specific software versions. 5.5 Practical application. Setting up a development environment. Let's say you're a web developer starting a new project that requires Node.js and its package manager, npm. Search for Node.js. Apt search Nodejs. You might find Nodejs and npm packages. However, the versions in the official Ubuntu repositories might be older than what you need for modern development. Add a specific Node.js PPA, common developer scenario. A common way to get recent Node.js versions on Ubuntu is via a PPA maintained by NodeSource. You'd get the specific PPA command from NodeSource's documentation, but for example, curl fssl https deb.nodesource.com/setup_ltsx sudo ebash. This command downloads a script and executes it with sudo, which adds the NodeSource repository. Then it automatically runs sudo apt update. Install Node.js and npm. Sudo apt install Nodejs. --npm is typically included with the Nodejs package now. Verify installation, node v. npm v. Now you have a specific, up-to-date version of Node.js and npm installed system-wide, all managed seamlessly by apt. This demonstrates how package managers simplify setting up complex development environments. By mastering your distribution's package manager, you gain immense control over the software on your system, ensuring your tools are always up-to-date, correctly configured, and easily managed. In the next chapter, we'll continue exploring essential developer tools by diving into the world of text editors, a developer's most intimate interface with code. 6. Mastering text editing. From Nano to NeoVim. If the command line is your development hub, then the text editor is the forge where you craft your code. As a developer on Linux, you'll spend an immense amount of time interacting with text files, whether writing code, configuring applications, drafting documentation, or debugging logs. While graphical text editors exist, Linux offers powerful, often terminal-based, editors that streamline workflows and integrate seamlessly with command line tools. This chapter will guide you through the fundamental text editing options available on Linux. We'll start with the simplest, Nano, for quick edits, and then introduce you to the mighty Vim and its modern derivative, NeoVim, an editor that, despite its steep learning curve, offers unparalleled efficiency and extensibility for professional developers. 6.1 The importance of a good text editor. A text editor is more than just a place to type words. For developers, a good editor is efficient, allows rapid navigation, editing, and manipulation of code. Extensible, can be customized with plugins, themes, and configurations to suit different languages and workflows. Integrated, works well with version control systems, build tools, and debuggers. Ubiquitous, Available on virtually any Linux system, including headless servers where a GUI is absent. 6.2 Nano, the friendly editor for quick edits. Nano is a simple, easy-to-use command-line text editor. It's often the default editor in many Linux distributions and is perfect for quick configuration file edits, writing short scripts, or for users who are new to CLI editors and don't want the immediate complexity of Vim. 6.2.1 Opening and basic editing with Nano. To open a file with Nano, simply type Nano followed by the file name. Nano sh. If the file doesn't exist, Nano will create it. Once inside Nano, you'll see the file content, and at the bottom of the screen, there's a helpful list of commands. These commands are typically activated by pressing Ctrl along with a letter. The caret symbol denotes the Control key. Typing, just start typing. It works like any basic text editor. Navigation, use the arrow keys to move the cursor. Saving changes, press Ctrl+O right out to save your changes. Nano will ask you to confirm the file name. Press Enter. Exiting Nano, press Ctrl+X exit. If you have unsaved changes, Nano will ask if you want to save them. Press Y for yes, N for no, or ESC to cancel. 6.2.2 Common Nano commands. Command action. Ctrl+G, get help. Ctrl+O write out, save file. Ctrl+X exit Nano. Ctrl+C cancel current command. Ctrl+W where is search. Ctrl+Y prev page. Ctrl+V next page. Ctrl+K cut line. Ctrl+U uncut paste. Nano is great for beginners and simple tasks, but its capabilities are limited when it comes to more advanced code manipulation, which is where editors like Vim truly shine. 6.3 Vimneo Vim, the developer's power tool. Vim Vi Improved is a highly configurable text editor that provides efficient text editing through modal editing. It's an enhanced version of the original Roman 6 editor, which has been a staple in Unix-like systems for decades. NeoVim is a modern, actively developed fork of Vim, aiming to improve its extensibility and integration. Most of what you learn for Vim will apply directly to NeoVim. Vim's power comes from its modal nature: normal mode, command mode. This is the default mode when you open Vim. In this mode, keystrokes are interpreted as commands, e.g., dd to delete a line, y to copy a line. You don't type text directly here. Insert mode. In this mode, keystrokes are interpreted as text to be inserted into the file. This is where you actually type your code. Visual mode, used for selecting blocks of text to apply commands to, e.g., visual block selection for multi-line edits. Command line mode, X mode, used for entering specific commands, often starting with, e.g., W to write save, Q to quit, S for substitute. The learning curve for Vim is notoriously steep, but the payoff in efficiency, especially for tasks involving repeated text manipulation, is immense. It's like learning to touch type for coding. Once you master it, it becomes second nature, and you rarely have to move your hands from the keyboard. 6.3.1 First steps with Vim. Opening a file. Vim MyCodePy. You'll enter normal mode. You cannot type code yet. Entering insert mode. To start typing, you need to enter insert mode. Common ways: I. Insert before the cursor, most common. Append after the cursor. O. Open a new line below the current one and enter insert mode. O. Open a new line above the current one and enter insert mode. Typing and navigating in insert mode. Once in insert mode, you can type text and use arrow keys, though Vim encourages movement commands in normal mode. Exiting insert mode back to normal mode. Press the ESC key. This is a critical habit to form. Always return to normal mode after typing. Saving and exiting from normal mode. W then enter, writes, saves the file. Q then enter, quits Vim if no changes or changes saved. WQ then enter. Writes, saves, and quits. X then enter, same as WQ. Q then enter, quits without saving changes, force quit. Use with caution. 6.3.2 Essential Vim Navigation, Normal Mode. Vim's greatest strength is its navigation. Often done using the H, J, K, L keys, left, down, up, right instead of arrow keys, allowing your hands to stay on the home row. Command action. H move cursor left. J move cursor down. K move cursor up. L move cursor right. W. Move to the beginning of the next word. B. Move to the beginning of the previous word. E. Move to the end of the next word. 0. Move to the beginning of the line. Move to the end of the line. GG. Go to the first line of the file. G. Go to the last line of the file. 5GG. Go to line 5 or any number. 6.3.3. Essential Vim Editing Normal Mode. This is where Vim feels like programming your edits. Commands often follow a number motion pattern. Command action example. X delete character under cursor. DD delete current line. 5DD deletes 5 lines. DW delete word from cursor to end of word. DO delete inner word, deletes whole word under cursor. D dollar delete from cursor to end of line. Y yank copy current line 3 Y copies 3 lines. IL yank copy word. P paste after cursor or below line. P paste before cursor or above line. U undo last chain. Control plus R redo last chain. Repeat last chain. Pattern search for pattern press N for next match. Error. %s old new G substitute old with new globally in file. %s/foo/bar/G. 6.3.4 Vim configuration. The vimrc file. Vim's power is unlocked through its extensive configuration options. Stored in a file called vimrc in your home directory /vimrc. NeoVim uses /config /nvim /initvim. Here are some common, useful settings to put in your vimrc. Set tabs to 4 spaces. Set tab stop equals 4. Set shift width equals 4. Set expand tab. Enable syntax highlighting. Syntax on. Show line numbers. Set number. Enable mouse support, convenient in terminal. Set mouse equals A. Enable fuzzy searching for files, often requires plugins. Set path plus equals. Set wild menu. After editing vimrc, save the file, then open Vim and type source % to reload the config, or simply restart Vim. 6.3.5 Neo Vim and plugins. NeoVim aims to be a more modern and extensible Vim. While core usage is the same, NeoVim has better default settings and a more robust plugin architecture. Modern Vim and NeoVim users often rely heavily on plugins for features like Fuzzy File Finder, for quickly opening files by typing partial names, e.g., FZFVim. Language Server Protocol (LSB) integration, providing IDE-like features, auto-completion, diagnostics, go-to definition for various programming languages. Git integration, showing Git status in the editor, e.g., FugitiveVim. Tree Explorer, a file tree panel, e.g., NerdTree. Learning to install and configure plugins is an advanced topic, often involving plugin managers like Vimplug or PackerNVim, but it's where Vim/NeoVim truly transforms into a highly personalized and powerful development environment. 6.4 Choosing your editor and practicing. You don't need to master Vim on day one. Many developers start with Nano for simple tasks, use a graphical editor like Visual Studio Code, which has excellent Linux support and a built-in terminal, and slowly learn Vim for efficiency. Practical advice: for quick config edits on a server, Nano is your friend. For everyday coding on a desktop, a modern graphical editor like VS Code or Sublime Text is excellent. They integrate well with the Linux environment. For maximum efficiency and remote work, start learning Vim. There are interactive tutorials like VimTutor, just type VimTutor in your terminal, that are a fantastic starting point. Commit to learning a few new commands each day. The key is to find an editor that suits your workflow and helps you be productive. For most professional Linux developers, Vim or NeoVim ultimately becomes an indispensable part of their toolkit due to its speed, customization, and availability on any system. In the next chapter, we'll leverage our command line and editing skills to automate tasks using shell scripting. 7. Automating tasks. Introduction to shell scripting. You've explored the Linux file system, navigated the command line, and started to master your text editor. Now, it's time to unlock one of the most powerful capabilities of the Linux environment: shell scripting. If you find yourself repeatedly typing a sequence of commands, shell scripting is your key to automation, efficiency, and consistency. For developers, shell scripts are indispensable. They are used for everything from simple file management and system maintenance to complex build processes, deployment automation, and testing workflows. This chapter will introduce you to the fundamentals of shell scripting using Bash, born again shell, the default shell on most Linux distributions. 7.1 What is a shell script? A shell script is simply a text file containing a sequence of commands that the shell can execute. Instead of typing each command one by one into the terminal, you can write them all down in a script file and then execute the entire script. Think of it like writing a recipe. You list the ingredients, commands, and the steps in order. When you run the script, the computer follows your recipe. Why use shell scripting? Automation of repetitive tasks. Eliminate manual keystrokes for daily operations. Consistency. Ensure tasks are performed the same way every time, reducing human error. Efficiency. Execute complex sequences of operations rapidly. System administration. Essential for managing servers, setting up cron jobs, scheduled tasks, and backing up data. Development workflows. Automating build steps, running tests, deploying code, and setting up development environments. 7.2 Your first shell script. Hello, developer. Let's create a simple script. Open your text editor, use Nano or Vim to create a new file. Nano HelloScript.sh. Write the script. Type the following lines into the file. Bin bash. Hash my first shell script. Echo hello developer. Echo, this is my first shell script in Linux. Bin bash shebang. This is the very first line of almost every shell script. It's called a shebang, from hash and bang. It tells the operating system which interpreter to use to execute the script. In this case, bin bash points to the bash shell. Hash my first shell script comments. Lines starting with hash are comments. The shell ignores them. Use comments to explain what your script does, making it easier for others and your future self to understand. Echo, this command prints text to the standard output, your terminal screen. Save and exit. Save the file, e.g., Ctrl+O, Enter, Ctrl+X in Nano. Make the script executable. By default, new files are not executable. You need to grant execute permissions using chmod. Chmod plus X HelloScript.sh. Recall from Chapter 4. Plus X adds execute permission for the owner, group, and others. Run the script. You can run the script in two ways, using its full path, relative or absolute. /HelloScript.sh. The is important. It tells the shell to look for the script in the current directory. By explicitly calling the interpreter, less common if shebang is correct, but useful for testing, bash HelloScript.sh. You should see, hello developer. This is my first shell script in Linux. 7.3 Variables and user input. Scripts become more powerful when they can handle dynamic data. Variables. Variables are used to store data, like text or numbers. In Bash, you define a variable by giving it a name and assigning a value, without spaces around the equals sign. To use the value of a variable, prefix its name with a sign. Bin bash. Script demonstrating variables. Name equals Alice. Age equals 30. Echo hello name. Echo name is age years old. You can also assign the output of a command to a variable using backticks or command. Current dir equals $pwd. Echo you are currently in. currentdir. Variables are case sensitive. Name is different from name. When using variables within strings enclosed in double quotes, they are expanded. Variables in single quotes are treated as literal text. User input. You can prompt the user for input using the read command. Bin bash. Script demonstrating user input. Read p what is your name? Username. Echo nice to meet you username. Read p enter your favorite programming language. Lang. Echo Lang is a great choice. Read p prompt. Variable displays a prompt and waits for the user to type something and press enter. The input is stored in Variable. 7.4 Control flow. Conditionals and loops. Like programming languages, shell scripting supports control flow structures to make decisions and repeat actions. Conditionals, if, elif, else. The if statement allows your script to execute different commands based on whether a condition is true or false. Bin bash. Script demonstrating if else. Read p enter a number, num. If num gt10, then. Echo the number is greater than 10. Elif num ec 10. Then. Echo the number is exactly 10. Else. Echo the number is less than 10. Example for checking if a file exists. file equals myfile.txt. If f file, then echo file exists. Else, echo file does not exist. Phi, test command used for evaluating conditions. Note the spaces around the brackets and operators are required. Operators. GT greater than, LT less than, EC equal to, NI not equal to for numbers. Equals not equal for strings. F is a regular file, D is a directory, E exists. Then and phi. Then introduces the commands to execute if the condition is true, and phi, if backwards, closes the if block. Loops for while. Loops allow you to repeat a block of commands multiple times. For loop, iterates over a list of items. Bin bash. Hash script demonstrating for loop. Echo, listing files in current directory. For file in ls, do. Echo file. Done. Echo counting from 1 to 3. For I in 1, 2, 3. Do. Echo count I. Done. ls command substitution. The ls command is executed, and its output list of files becomes the list for the for loop. While loop repeats commands as long as a condition is true. Bin bash. Hash script demonstrating while loop. Count equals 1. While count l5 do. Echo current count, count. Count equals $count plus 1, hash arithmetic operation. Sleep 1 hash pause for 1 second. Done. Echo loop finished. Sleep 1. A command to pause script execution for a specified number of seconds. 7.5 Functions and arguments. For larger scripts, it's good practice to organize code into functions to improve readability and reusability. Scripts can also accept arguments when executed. Functions. Functions are blocks of code that can be called by name. Bin bash. Script demonstrating functions. Greeduser. Echo hello $1. Echo welcome to the shell scripting world. Call the function passing developer as the first argument. Greeduser developer. Echo script finished. $1, $2, etc. Within the function, refer to the arguments passed to the function when it's called. $1 is the first argument, $2 is the second, and so on. Script arguments. Your main script can also accept arguments directly from the command line when it's executed. These are also referred to as $1, $2, etc., but apply to the arguments passed to the script itself. $0 refers to the script name. Bin bash. Script demonstrating script arguments. Echo script name. $0. Echo first argument, $1. Echo second argument, $2. Echo all arguments. Echo number of arguments. Example usage. /miscript sh arg1 arg2. Run this script, /miscript sh apple banana. Output script name, /miscript sh. First argument, apple. Second argument, banana. All arguments, apple banana. Number of arguments, 2. 7.6 Practical Shell Scripting for Developers. Here are some real-world examples of how developers use shell scripts. Project Setup Script. A script to clone a Git repository. Install dependencies, e.g. npm install, pip install. Create necessary config files and start a development server. Bin bash. Hash setup project sh. reprl equals $1. If z rep URL, then echo usage /setup project sh reprl. Exit 1. Phi. Projectdir equals $base name rep URL. Git. If d projctdir. Then echo error. Directory projctdir already exists. Exit 1. Phi. Echo cloning repo URL into projctdir. Git clone repo URL, projctdir, echo git clone failed. Exit 1. cd projctdir, echo failed to change directory. Exit 1. Echo installing Node.js dependencies. npm install, echo npm install failed. Exit 1. Echo project setup complete. Run npm start to begin development. Backup script. A script to compress an important directory and move it to a backup location. Bin bash. Hash backup data sh. Backupdir equals /mnt/backup /mydata. Sourcedir equals /home/your username /important projects. Timestamp equals $date plus %y%m%d%h%m%s. Archive name equals projects backup $timestamp tar gz. mkdir p basicopdir. Echo creating backup of sourcdir. tar czf backup dir /$ archive name, sourcdir. If x0 then echo backup created successfully, backavedir /$ archive name, else echo backup failed, phi returns the exit status of the last executed command. Usually means success, non-zero indicates an error. Log cleanup, a script to delete old log files. Shell scripting is a vast topic, but these fundamentals provide a solid starting point for automating basic tasks. As you become more comfortable, you'll discover complex scenarios where scripting can save you countless hours. Always start simple, test frequently, and add comments to your scripts. In the next chapter, we'll continue our exploration of essential Linux tools by learning how to manage processes and services running on your system. 8. Working with processes and services. As a developer, you're not just writing code. You're also interacting with running programs, often called processes, and managing system-level services that run in the background. Understanding how to monitor, control, and troubleshoot processes and services is crucial for debugging applications, managing server resources, and ensuring your development environment, and eventually your deployed applications, runs smoothly. This chapter will teach you how to view running processes, terminate misbehaving ones, manage system services, and interpret basic system load information. 8.1 What are processes and services? Process. A process is simply an instance of a running computer program. When you launch an application, open a terminal, or even run a shell script, a process, or often multiple processes, is created. Each process is assigned a unique process ID, PID. Service or daemon. A service, often called a daemon in Unix-like systems, such as HTTPD for an Apache web server or SSHD for the SSH daemon, is a type of process that runs continuously in the background, typically without user interaction. Services provide core functionalities of the operating system or applications, such as web serving, database management, logging, or network access. Services are often started automatically at bootup. 8.2 Viewing running processes. The PS and top commands are your primary tools for inspecting processes. PS, process status. The PS command displays a snapshot of the current processes. PS aux. This is one of the most commonly used combinations. Show processes for all users. U, display user owner and other detailed information. X, show processes not controlled by a terminal daemon processes. PS aux. You'll see a lot of output, typically with columns like user, the user who owns the process. PID, the unique process ID. %CPU, the percentage of CPU time the process is currently using. %MEM, the percentage of physical memory the process is currently using. VSC, virtual memory size total virtual memory used by the process. RSS, resident set size, physical memory the process is currently using, a subset of VSC. TTY, the terminal associated with the process, means no terminal. Stat, current state of the process, e.g. R for running, S for sleeping, Z for zombie, T for stopped. Start, time the process started. Time, total CPU time the process has consumed. Command, the command that launched the process, including arguments. PSF, another common combined option, similar to PS aux but with a slightly different output format. It shows processes in a full listing format. Top, table of processes. While PS gives you a snapshot, Top provides a real-time, dynamic view of running processes. It's excellent for monitoring system, resource usage, and identifying resource-hungry processes. Top. In the Top interface, the top section shows a summary of system performance, load average. 3 numbers representing the average number of processes waiting to run in the last 1, 5, and 15 minutes. High numbers indicate a busy system. Tasks, total number of processes, and how many are running, sleeping, stopped, or zombie. CPU, percentage breakdown of CPU usage, user, system, idle, etc. Mem and swap, total, used, and free physical memory and swap space. The main section lists processes sorted by CPU usage by default. You can sort by different columns by pressing keys like P, CPU usage, default, M, memory usage. Press K to kill a process. It will prompt for PID. Press Q to quit top. HTOP Interactive Process Viewer. HTOP is an enhanced and more user-friendly version of top. It's not usually installed by default, but it's a favorite among developers and system administrators. Sudo apt install HTOP. HTOP provides color-coded output, easy vertical and horizontal scrolling to see all processes and command lines, visual CPU memory meters, interactive mouse and function key support for sorting, filtering, and killing processes. Press F9 for kill menu, F10 or Q to quit. 8.3 Terminating processes, killing processes. Sometimes, a process might become unresponsive, consume too many resources, or needs to be stopped gracefully. The kill command is used for this. It sends a signal to a process. Kill PID, the default signal is SIGTERM, signal 15, which politely asks the process to shut down. The process can ignore this signal if it's too busy or buggy. Find the PID of the process using PSAUX or top/HTOP. Execute kill PID. Hash example. If HTOP shows a process with PID 12,345, kill 12,345. Kill -9 PID, force kill /SIGKILL. This sends SIGKILL, signal 9, which immediately terminates the process without giving it a chance to clean up or save data. Use this as a last resort, as it can lead to data corruption or orphan temporary files. Kill -9, 12,345. pkill and killall. pkill pattern kills processes by name or other attributes. It matches processes by their full command line. pkill Firefox hash kills all Firefox processes. pkill mistacap hashforce kills processes matching mistacap. Killall process name kills processes by their exact name. Killall Chrome hash kills all processes named Chrome. Always be cautious when using pkill or killall, especially with -9, as you might accidentally kill critical system processes or multiple applications. 8.4 Managing services with systemd. Most modern Linux distributions, including Ubuntu, use systemd as their init system. Systemd manages system services, starting them at boot, restarting them if they crash, and stopping them cleanly. The primary command line tool for interacting with systemd is systemd. Important, systemd commands usually require sudo start a service, sudo systemd start service name. Hash example, start the nginx web server, sudo systemd start nginx. Stop a service, sudo systemd stop service name. Hash example, stop the nginx web server, sudo systemd stop nginx. Restart a service. This stops and then starts the service. Useful for applying configuration changes. Sudo systemd restart service name. Hash example, apply new nginx config. Sudo systemd restart nginx. Reload a service. Some services can reload their configuration without a full restart, avoiding downtime. Sudo systemd reload service name. Hash example, reload nginx without interrupting active connections. Sudo systemd reload nginx. Check service status. See if a service is running, its process ID, and recent log messages. Sudo systemd status service name. Hash example, sudo systemd status nginx. This output is invaluable for debugging why a service might not be starting or is crashing. Press Q to exit. Enable a service, start at boot, ensures the service starts automatically when the system boots. Sudo systemd enable service name. Hash example, make nginx start at boot. Sudo systemd enable nginx. Disable a service, don't start at boot, prevents the service from starting automatically. Sudo systemd disable service name. List all running services. Systemd list units, type equals service state equals running. 8.5 Running commands in the background. Sometimes you'll want to run a command or script without tying up your terminal. Appending end. The simplest way to run a command in the background is to append and to the end of the command. /mylongscript.sh end. The terminal will give you a PID, process ID, and a job ID, e.g., 1/12,345. You can continue using your terminal. However, if you close the terminal, the background process might be terminated. No hup, no hang-up. To ensure a process continues to run even if you close the terminal or log out, use nohup. Nohup /mylongscript.sh end. The output of mylong_script.sh will be redirected to a file named nohupout in the current directory by default. Ctrl+Z, suspend. If you've started a command and realize you want to background it, press Ctrl+Z. This will suspend the process. /mylong_script.sh hash start the script. Z hash press Ctrl+Z. Hash output, 1 plus stopped, /mylong_script.sh. Then, to put it in the background, bg hash puts the last suspended job in the background. To bring a background job back to the foreground, fg hash brings the last background job to foreground. fg% job at hash e.g. fg%1. You can see currently active jobs using the jobs command. 8.6 Practical application. Debugging a stalled web server. Imagine you're running a local development web server, e.g. Node.js app, Python Flask app, and it becomes unresponsive. Identify the process. You might know the port e.g. 3000 for Node.js. Use elseof I 3000 or netstat-tulp grep 3000 to find its PID. Or you might remember the command used to start it. ps-aux grep node hash or Python, Flask, etc. Alternatively, use htop to sort by CPU memory and look for your app. Examine its status. If using systemctl, like Nginx, Apache, or a custom system service, sudo systemctl status mywebservice. Look for error messages or active. Failed. If running the app manually, check top/htop for high CPU usage, or if it's stuck in a sleeping or uninterruptible state. Attempt a graceful restart kill. If it's a system service, sudo systemctl restart mywebservice. If it's a manually run process, and you found its PID, say 12,345, kill 12,345, hash send sigtrm. If all else fails, force kill. If kill doesn't work after a few seconds, use kill -9 12,345 hash send sigkill. Then you can restart your application. Mastering process and service management gives you deep insight into how your Linux system is performing and enables you to effectively control the runtime environment for your applications. This foundational knowledge is key to both local development and managing deployed applications on servers. In the next chapter, we'll shift our focus to networking concepts within Linux, an essential skill for any developer building connected applications. 9. Linux networking, connecting your code. In the interconnected world of software development, networking is not just an optional extra, it's a core component. Whether you're building a web application, consuming APIs, deploying to the cloud, or simply accessing resources on your local network, a solid understanding of Linux networking is invaluable. This chapter will demystify essential networking concepts and introduce you to the command line tools that allow you to diagnose connections, configure network interfaces, and ensure your applications can communicate effectively. We'll primarily focus on tools that are universally available on most Linux systems. 9.1 Fundamental networking concepts. Before diving into commands, let's briefly review some key networking terms. IP address, Internet Protocol address, a numerical label assigned to each device connected to a computer network that uses the Internet Protocol for communication. IP4, 4 sets of numbers separated by dots, e.g., 192.168.1.100. IP6, a newer, longer address format designed to accommodate more devices, e.g., 2001, 0DB8, 85A3, 0000, AE, 707334. Subnet mask, used to divide an IP address into two parts, the network address and the host address. It determines which part of an IP address identifies the network and which part identifies the device on that network. Gateway router, a device, usually a router, that enables traffic to flow from one network to another. Your local network's gateway is the point your computer sends traffic to when it needs to reach the internet or another network. DNS, domain name system, a hierarchical and decentralized naming system for computers, services, or any resource connected to the internet or a private network. It translates human-readable domain names, e.g., google.com, into numerical IP addresses. Port, a communication endpoint in a computer's operating system. Applications listen for incoming network traffic on specific ports, e.g., HTTP sits on port 80, HTTPS on 443, SSH on 22. When you connect to an IP address, you also specify a port. Firewall, a network security system that monitors and controls incoming and outgoing network traffic based on predetermined security rules. Its purpose is to establish a barrier between a trusted internal network and untrusted external networks, like the Internet. Interface, NIC. A network interface card, NIC or network adapter, is hardware that connects your computer to a network. In Linux, these interfaces are represented by names like ETH0 for wired Ethernet or WLAN 0 for wireless LAN. Low loopback is a special interface for communicating with services on the same machine. 9.2. Checking your network configuration. Several commands allow you to inspect your system's network settings. IP, interface configuration. The IP command is the modern standard for displaying and configuring network devices, routing tables, and tunnels. It's highly versatile and largely replaces older tools like ifconfig and root. View IP addresses and network interfaces. IP address show. Hash or just IP? This shows all network interfaces on your system, e.g., low ETH0, WLAN 0, their IP addresses IP4 and IP6, MAC addresses and current status, UP, DOWN. View routing table. The routing table tells your system how to send traffic to different networks. IP route show. Hash or just IPR. Look for a line starting with default via, which indicates your default gateway. View neighbor table, ARP cache, shows the mapping between IP addresses and MAC addresses on your local network. IPNA show. Hostname, host, and domain name. The hostname command tells you your machine's network name. Hostname, your machine's hostname, e.g., your username VirtualBox. Resolvectal, DNS resolver information, to see which DNS servers your system is using and how it resolves domain names. Resolvectal status. This is useful for diagnosing DNS-related connection issues. 9.3. Diagnosing network connectivity. When a network application isn't working, these are your go-to diagnostic commands. Ping packet internet groper. Ping sends small data packets to a target IP address or hostname to test connectivity and measure response time. Ping google.com hash ping a website. Ping 8.8.8.8 hash ping Google's public DNS server. Ping 192.168.1.1 hash ping your local router gateway. Control+C to stop ping. Look for time equals to see latency, response time in milliseconds. Destination host unreachable or request timed out indicates a problem. Traceroute, trace route to host. Traceroute tracks the path a packet takes to reach a destination, showing each hop, router along the way. This is invaluable for identifying where a connection might be failing. Traceroute google.com. If you see asterisks at a particular hop, it means that router isn't responding, indicating a potential issue at that point. Netstat network statistics. SS socket statistics. These commands display network connections, routing tables, interface statistics, and more. SS is newer and often faster than Netstat. Show listening ports, what services are running and accessible. Sudo netstat tomp hash TCP, UDP, listening, numeric ports, programs. Sudo ss tomp. This output shows which programs are listening on which ports, e.g. Nginx listening on 0.0.0.0:80 means it's ready to accept HTTP connections on all network interfaces. Show all network connections. Sudo netstat amp hash all numeric programs. Sudo ss amp. This will list all established connections, showing source and destination IP addresses and ports. curl and wget web client tools. While not strictly network diagnosis tools, curl and wget are essential for testing web services and downloading resources from the command line. Curl, a powerful tool for making HTTP requests and many other protocols. Excellent for testing APIs. Curl https api.github.com/users/octocat hash make a get request and show response. Curl https www.google.com hash show only HTTP headers. Curl x post d. param1 equals value 1, http localhost:8080/API/data hash make a post request. wget, primarily used for downloading files from the web wget https example.com/softwarezip. 9.4 Firewall management with UFWA. Linux systems, especially development machines and servers, often have a firewall enabled to control network access. Ubuntu uses UFWA Uncomplicated Firewall as a front-end to NetFilter, the Linux kernel's packet filtering framework, making firewall management easier. Important: modifying firewall rules requires sudo. Incorrect firewall rules can lock you out of your system. Check firewall status. Sudo UFWA status verbose. Enable disable firewall. Sudo UFWA enable hash enables the firewall, careful if connecting via SSH. Sudo UFWA disable hash disables the firewall. Allow deny connections. Rules are processed from the top down. UFWA has default policies, e.g., deny incoming, allow outgoing. Allow SSH port 22, essential if you're connecting remotely. Sudo UFWA allow SSH. Hash or sudo UFWA allow 22. Allow HTTP port 80 for web servers. Sudo UFWA allow HTTP. Hash or sudo UFWA allow 80/TCP. Allow HTTPS port 443. Sudo UFWA allow HTTPS. Hash or sudo UFWA allow 443/TCP. Allow a specific port protocol. Sudo UFWA allow 8080/TCP. Hash allow inbound TCP traffic on port 8080. Sudo UFWA deny 25/TCP hash, deny outbound SMTP traffic. Example: allow from a specific IP address. Sudo UFWA allow from 192.168.1.100 to any port SSH. Delete a rule. Sudo UFWA status numbered hash get rule numbers. Sudo UFWA delete rule number. 9.5 Practical scenario. Setting up a local web server. Let's combine some of these concepts to ensure your Node.js application, running on port 3000, is accessible from other machines on your local network. Start your Node.js application, assuming it listens on localhost :3000. Verify it's listening locally. Sudo ss-tomp grep 3000. You should see an entry like TCP listen 0, 5127.0.0.1:3000. The 127.0.0.1 means it's only listening locally. Loopback. Adjust your Node.js app to listen on all interfaces. Most development servers have an option to bind to 0.0.0.0 or your localip. Change your app's configuration to port and host with host equals 0.0.0.0. Restart your app. Confirm it's listening externally. Sudo ss-tomp grep 3000. Now you should see 0.0.0.0:3000 or your localip 3000, indicating it's accessible externally. Check firewall status, sudo UFWA status. If it's active and not allowing port 3000, other machines can't connect. Allow port 3000 through the firewall. Sudo UFWA allow 3000/TCP. Test from another machine. Open a browser on another computer on the same network and type http:// your Linux IP address 3000. You should see your Node.js application. Find your Linux IP with IP. Understanding Linux networking is no longer just for system administrators. As developers increasingly work with microservices, cloud deployments, and remote APIs, being able to troubleshoot network issues and configure connectivity from the command line is a valuable skill. In the next chapter, we'll shift our focus to version control, specifically Git, which is inseparable from modern development on any operating system, including Linux. 10. Version control with Git on Linux. For any serious software developer, version control is not just a useful tool, it's an absolute necessity. It allows you to track changes to your code, collaborate with others, revert to previous versions, and manage different lines of development through branching. While several version control systems exist, Git has become the undisputed industry standard. Linux provides the perfect environment for working with Git. In fact, Git itself was created by Linus Torvalds, the creator of Linux, to manage the development of the Linux kernel. This chapter will guide you through setting up and using Git on your Linux system, covering essential commands for managing your code. 10.1 What is version control and why Git? Imagine working on a project without saving multiple versions of your work. If you make a mistake, you might lose hours or days of effort. If you're collaborating with others, how do you merge everyone's changes without overwriting each other's work? This is the problem version control solves. Version Control System, VCS, a system that records changes to a file or set of files over time so that you can recall specific versions later. Git, a distributed version control system, DVCS. This means every developer's working copy of the code is a complete repository in itself, including the full history of the project. Unlike centralized systems, like SVN, you don't always need a network connection to commit changes. Key advantages of Git. Speed. Git is incredibly fast. Distributed nature. Local repositories provide offline capabilities and resilience. Branching and merging. Git's branching model is lightweight and allows for easy experimentation and parallel development. Data integrity. Content is cryptographically hashed, ensuring no accidental corruption. Popularity. It's the standard, meaning vast community support and integration with numerous platforms, GitHub, GitLab, Bitbucket. 10.2 Installing Git on Linux. Git is usually available in the official repositories of most Linux distributions. On Ubuntu/Debian-based systems, you can install it using apt. Sudo apt update. Sudo apt install Git. After installation, verify Git is installed and check its version. Git version. 10.3 Initial Git configuration. Before you start using Git, you need to configure your identity. This information will be attached to your commits, identifying who made each change. Git config global user.name, your name. Git config global user email, your email at example.com. Global. This flag means the configuration applies to all your Git repositories on this system. You can set project-specific configurations by omitting global and running the commands inside a repository. You might also want to configure your default text editor for Git used for commit messages. If you prefer Vim, as we discussed in Chapter 6, this is a good default. Git config, global core editor Vim. Or if you prefer Nano, Git config, global core editor Nano. To view your current Git configuration, Git config list. 10.4 Basic Git workflow, a local repository. Let's start by creating a new Git repository locally. Create a project directory, mkdir minoproject, cd minoproject. Initialize a Git repository, git init. This command creates a new, empty Git repository in the current directory, usually a hidden Git subdirectory. Create some files. Use your text editor to create some simple files. Index.html, doc2ip HTML, HTML lang equals n. Head, meta charset equals UTF-8. Meta name equals viewport, content equals width equals device width. Initial scale equals 1.0. Title my first project title. Head, body, h1 welcome to my project /h1. Body, HTML, style CSS. Body, font family, sans serif background color, light blue. Check status. The git status command shows the state of your working directory and staging area. Git status. Output, on branch master hash or main, depending on Git version. No commits yet. Untracked files, use git add file to include in what will be committed. Index.html, style CSS. Nothing added to commit but untracked files present. Use git add to track. Untracked files means Git sees them but isn't yet managing their versions. Stage files add to index. The staging area, or index, is an intermediate area where you prepare changes before committing them. Git add index.html style CSS. Hash or to add all new modified files in the current directory. Hash git add, check status again, git status. Output on branch master. No commits yet. Changes to be committed. Use git rm cached file to unstage. New file, index.html. New file, style CSS. Now the files are staged and ready to be committed. Commit changes. A commit is a snapshot of your repository at a specific point in time. Each commit has a commit message describing the changes. Git commit m, initial project setup with basic HTML and CSS. M provides the commit message directly. If you omit M, Git will open your default text editor, e.g., Vim or Nano, for you to write the commit message. Check log, view the commit history, Git log. You'll see your commit, including the author, date, and commit message. 10.5 Making changes and committing. Let's make a change and commit it. Modify a file. Edit index.html to add a paragraph. DiositYP HTML. HTML lang equals n. Head. Meta charset equals UTF-8. Meta name equals viewport. Content equals width equals device width. Initial scale equals 1.0. Title my first project title. Head. Body. H1 Welcome to my project /H1. P This is a new paragraph, added in the first modification P. Body. HTML. Check status. Git status. Output on branch master. Changes not staged for commit. Use git add file to update what will be committed. Use git restore file to discard changes in working directory. Modified. Index.html. No changes added to commit. Use git add and or git commit a. Git shows that index.html has been modified but not yet staged. Stage and commit. Git add index.html. Git commit m. Add new paragraph to index.html. 10.6 Inspecting changes. Git diff shows changes in your working directory that are not yet staged. Git diff. Git diff staged or git diff cached shows changes in the staging area that are not yet committed. Git diff staged. Git diff head shows changes in your working directory that are not yet committed against the last commit. 10.7 Branching and merging. Branching is essential for collaborative development and managing features. Git branch, list branches, git branch, hash master or main. The indicates your current branch. Git branch name. Create a new branch, git branch feature footer. Git checkout branch name, switch to another branch. Git checkout feature footer. You can also combine creating and switching. Git checkout b feature contact pay. Now on the feature footer branch, edit index.html and add a footer. Body. H1 Welcome to my project /H1. P This is a new paragraph, added in the first modification P. Footer. P and copy. 2023 My project P. Footer. Body. HTML. Stage and commit your changes on this new branch. Git add index.html. Git commit m. Add simple footer. Now switch back to your master or main branch. Git checkout master. You'll notice the footer is gone from index.html. This is because the change was made on the feature footer branch. Git merge branch name. Merge changes from another branch into your current branch. Git merge feature footer. Git will attempt to merge the changes. If there are no conflicts, it will create a new merge commit. If conflicts occur, when the same lines are changed differently in both branches, Git will tell you, and you'll need to manually resolve them in the affected files before committing. Git will mark the conflicting sections. Git branch d branch name. Delete a branch only after it's merged. Use D to force delete an unmerged branch. Git branch d feature footer. 10.8 Working with remote repositories. GitHub GitLab. Most real-world projects are hosted on remote Git services like GitHub, GitLab, or Bitbucket. Create a new repository on GitHub GitLab. Go to your chosen platform, log in, and create a new empty repository. Do not initialize it with a README or license file yet, as it will cause conflicts when pushing your existing local history. Add a remote origin. Link your local repository to the remote one. Replace the example URL with your repository's URL. Git remote add origin https github.com/username/minuprojectgit. Origin is the default name for the primary remote. Push changes to remote. Send your local commits to the remote repository. Git push u origin master. Hash the u flag or set upstream. Sets the upstream branch, so future pushes and pulls are simpler, just git push or git pull. You'll be prompted for your GitHub GitLab username and password personal access token. Pull changes from remote. Download changes from the remote repository to your local one. Git pull origin master. This is crucial when collaborating to ensure you have the latest code. 10.9 Ignoring files with gitignore. Not all files in your project directory should be version controlled by Git. Examples include compiled binaries, e.g. class, exe, dependency modules, e.g. node module/vemp/, IDE configuration files, log files, sensitive data, e.g., API keys, database credentials. You can tell Git to ignore these files by creating a file named gitignore in your project's root directory. Create gitignore, nano gitignore. Add patterns, #ignore all node modules directories. Node modules, #ignore all compiled Python files. Pick, #ignore env files for environment variables. Env, #ignore log files. Log, logs, #ignore IDE specific files. Idea, vscode. Commit gitignore to your repository so everyone collaborating uses the same rules. Git is an incredibly powerful and nuanced tool. This chapter only scratches the surface of its capabilities. Features like stashing, rebasing, bisecting, and using interactive rebase offer even more control over your commit history. However, mastering these basic commands is more than enough to handle most daily development tasks and collaborate effectively within a team environment using Git on Linux. In the next chapter, we'll dive into another critical aspect of modern development: creating isolated and consistent development environments using tools like Docker, virtual machines, and WSL11. Development environments, Docker, VMS, and WSL. As developers, we often work on multiple projects, each with its own set of dependencies, programming language versions, and operating system requirements. This can lead to the dreaded "it works on my machine" problem, where a piece of code functions perfectly on one developer's computer but fails on another's, or worse, in production. This chapter explores modern strategies for creating consistent, reproducible, and isolated development environments on Linux, focusing on Docker for containerization, virtual machines, VMS for full OS isolation, and Windows Subsystem for Linux, WSL for Windows integration. Understanding these tools is crucial for streamlining your workflow, ensuring project stability, and bridging the gap between development and deployment. 11.1 The challenge of development environment consistency. Consider these common scenarios. Project A requires Python 3.8 and PostgreSQL 12. Project B requires Python 3.10 and PostgreSQL 14. Your colleague uses macOS, while you prefer Linux. Your production server runs a specific version of Node.js and a particular Linux distribution. Without proper isolation, managing these conflicting requirements on a single machine quickly becomes a nightmare. Updating one dependency for project A might break project B. The solutions typically revolve around creating isolated environments. 11.2 Virtual machines, VMS, for full OS isolation. As introduced in Chapter 2, a virtual machine, VM, runs a complete independent operating system, the guest OS, on top of your existing operating system, the host OS. It virtualizes hardware components like CPU, RAM, and storage, making the guest OS believe it's running on physical hardware. Pros for development: complete isolation. Each VM is a completely separate operating system environment. You can have VMS running different Linux distributions, older OS versions, or even Windows within your Linux host. Reproducibility. Once a VM is configured, it can be stopped, copied, and shared, ensuring everyone on your team works with an identical environment. Production parity. You can create VMS that precisely mirror your production server environment, same OS version, same libraries, reducing deployment surprises. Snapshots. You can easily save the state of a VM at any point and revert to it later, perfect for testing risky changes or recovering from mistakes. Cons for development: resource overhead. VMS consumes significant host resources, RAM, CPU, disk space, for each running instance because they virtualize an entire operating system. Slower startup. Booting up a VM takes time, similar to booting a physical computer. Lack of portability compared to containers. VM images, e.g. OVA, VMDK, can be large and cumbersome to distribute. Management complexity. Setting up and managing VMS, especially manually, can be more involved. Tools: VirtualBox, free, open source, and cross-platform, excellent for personal use and smaller teams. VMware Workstation Player Pro, popular commercial options with advanced features. KVM, kernel-based virtual machine, a built-in virtualization solution for Linux, offering near-native performance. often managed via tools like Virt Manager or libvirt. Vagrant, a tool for building and managing virtual machine environments. Vagrant works with providers like VirtualBox or KVM, allowing you to define your VM setup in a simple configuration file, Vagrant file. This makes VM creation and sharing much easier, bringing an element of infrastructure as code to VMs. 11.3 Windows Subsystem for Linux WSL for Windows integration. While this book focuses on Linux as your primary OS, many developers use Windows and leverage WSL to gain a powerful Linux command line environment without full virtualization. WSL allows you to run Linux distributions directly within Windows, offering strong integration between the two operating systems. Pros for development: seamless integration. Access Windows files directly from Linux, run Windows executables from the Linux shell, and use familiar Windows desktop apps. Lightweight. WSL2, the latest version, uses a lightweight utility VM, offering good performance with less overhead than a traditional VM. Convenience: easy to install multiple Linux distros from the Microsoft Store. Familiar Linux environment provides the full Linux command line benefits, packaging tools, scripting, etc. for Windows users. Cons for development: Windows dependency. You are still tied to the Windows ecosystem. Resource management: while lightweight, it still uses resources that can compete with other Windows applications. No full desktop Linux. Primarily a command line environment, running full Linux desktop applications can be challenging or performance limited. Not ideal for Linux native development. If your goal is to master Linux as your primary development OS, building directly on a native Linux installation or a VM on a Linux host is more authentic to the full Linux experience. Use cases: developers primarily on Windows who need a robust Linux command line for backend development, scripting, or using Linux native tools without a dual boot. 11.4 Docker for containerization. The modern standard. Docker has revolutionized how developers package, deploy, and run applications. At its core, Docker uses containers, lightweight, standalone, executable packages of software that include everything needed to run an application: code, runtime, system tools, libraries, and settings. Unlike VMS, containers share the host operating system's kernel, making them much faster to start and consume significantly fewer resources. 11.4.1 Key Docker concepts. Image, a lightweight, standalone, executable package that includes everything needed to run a piece of software, including the code, a runtime, libraries, environment variables, and config files. Images are built from a Docker file. Container, a runnable instance of an image. You can start, stop, move, or delete a container. Multiple containers can run from the same image. Docker file, a text file that contains all the commands a user could call on the command line to assemble an image. It's like a recipe for building your application's environment. Docker Hub, a cloud-based registry service where you can find and share Docker images, like GitHub for Docker images. 11.4.2 Installing Docker on Linux. Installation typically involves adding Docker's official repository and installing from there. Update package list. Sudo apt update. Install dependencies, only required once. Sudo apt install apt transport https ca certificates, curl software properties common. Add Docker's official GPG key. Curl fs sl https download.docker.com/linux/ubuntu/gpg sudo gpg dirmer o/usr/share/keyrings/docker archive keyring Set up the stable repository. Echo deb arch equals $dpkg print architecture. Signed by /usr/share/keyrings/docker archive keyring gpg. https download.docker.com/linux/ubuntu ls cs stable sudo t etc apt sources list d docker list dev/null. Update package list again. Sudo apt update. Install Docker engine. Sudo apt install dockerc dockercli container.io. Add your user to the Docker group to run Docker commands without sudo. Sudo usermod ag docker user. Log out and log back in or reboot for the group change to take effect. After logging back in, test your installation. Docker run hello world. This command downloads a test image and runs it in a container, printing a "Hello from Docker" message. 11.4.3 Essential Docker Commands for Developers. Docker pull image name. Downloads an image from Docker Hub. Docker pull Ubuntu. Latest hash downloads the latest Ubuntu image. Docker run image name. Creates and starts a new container from an image. Interactive and sudo tty for interactive shells. P host port, container port, maps a port from your host machine to a port inside the container. V host path, container path, mounts a volume, shares a directory from your host into the container. Essential for development, so code changes on your host are reflected in the container. Name container name, assigns a name to your container. D. Run container in detached mode background. Docker run at Ubuntu, latest bash hash run bash shell in a new Ubuntu container. Docker run p808080v/mywebapp /var/www/html name myengine x engine x hash run engine x map port mount code. Docker ps lists running containers. Docker psa lists all containers running and stopped. Docker stop containerid/name stops a running container. Docker start containerid/name starts a stopped container. Docker restart containerid/name restarts a container. Docker rm containerid/name removes a stopped container. Use F to force remove a running container, e.g., Docker rm f myengine x. Docker rmi imagid/name removes an image. Docker exec at containerid/name command runs a command inside a running container. Docker exec it myengine x bash hash get a shell inside the running engine x container. Docker logs containerid/name fetches logs from a container. Use F to follow logs in real time. 11.4.4 Dockerfile basics. A Dockerfile is a script containing instructions to build a Docker image. Use an official Node.js runtime as a parent image. From Node 18 Alpine. Set the working directory in the container. wrkdir app. Copy package.json and package.lock.json to working directory. Copy package.json yarn lock. Install app dependencies. Run yarn install production. Copy the rest of your app's source code. Copy. Expose the port your app runs on. Expose 3000. Define the command to run your app. cmd node src/index.js. To build an image from this Docker file in the same directory as the Docker file. Docker build tmynode app. Then you can run it. Docker run p303000 mynode app. 11.4.5 Docker compose for multi-container applications. Many applications consist of multiple services, e.g., a web app, a database, a cache. Docker Compose allows you to define and run multi-container Docker applications using a YAML file, Docker Compose YAML. Docker Compose YAML. Version 3.8. Services, web build, ports. 30.30.0. Volumes, app hash mount current directory into container for live dev reload. DB, image, Postgres 14 alp. Environment, postgresdb, mydb. postgresuser. User, postgresbsswrd. Password. Volumes, db data, /var/lib/postgresql/data. Volumes, db data. To bring up the entire application. Docker Compose up d-d for detached mode. To shut down. Docker Compose down. 11.5 Practical application. Choosing the right environment tool. For quick, safe Linux experimentation or for a consistent server environment locally. VMS, especially with Vagrant. For Windows users who need a powerful Linux terminal and toolchain integrated with their Windows files. WSL. For packaging applications, isolating dependencies across projects, ensuring production parity, and collaborative development. Docker and Docker Compose. This is the leading solution for modern application development. Containers have largely superseded VMS for application-level isolation due to their efficiency and speed, but VMS still have their place for full OS virtualization, e.g., running specific OS versions, legacy systems, or very different architectures. As Linux developers, being proficient with Docker is no longer optional, it's a core skill. In the next chapter, we'll delve into troubleshooting and performance monitoring, essential skills for keeping your Linux development environment and your applications running smoothly. 12. Troubleshooting and performance monitoring. Even with the most robust systems, things can go wrong. Applications crash, the system slows down, or a service mysteriously stops working. As a developer, the ability to diagnose problems and monitor system performance is as crucial as writing code. This chapter equips you with essential Linux commands and techniques to troubleshoot common issues and keep an eye on your system's health, ensuring your development environment and the applications you build runs smoothly. We'll focus on methods for identifying bottlenecks, errors, and understanding system behavior using built-in Linux tools. 12.1. Approaching troubleshooting. A systematic method. When a problem arises, a systematic approach helps you find solutions more efficiently. Understand the problem. What exactly is happening? What are the symptoms? When did it start? Was anything changed recently? Is it reproducible? How can you reliably make it happen? What is the expected behavior? Check logs. Almost every application and system service on Linux logs its activities. Logs are your first and best source of information. Check resources. Is the system running out of CPU, memory, or disk space? Are network connections congested? Isolate the issue. Is the problem with your code, a dependency, the operating system, or the network? Try to eliminate variables until you pinpoint the source. Search for solutions. Use search engines, Stack Overflow, and official documentation with specific error messages. Formulate a hypothesis. Based on your findings, what do you think is going wrong? Test the hypothesis. Try a potential solution. If it works, great. If not, gather more data and repeat the process. 12.2. Checking system logs. Logs are text files that record events from the system kernel, services, and applications. They often contain error messages, warnings, and informational messages that can point directly to the root cause of a problem. Journoctl System Journal. Modern Linux distributions using systemed, like Ubuntu, centralize logs into a system journal. This is your primary tool for system-wide logging. View all logs paginated. Journoctl. View logs from a specific service. Journoctl U Engine X service #view logs for Engine X. Journoctl U Docker service #view logs for Docker. View logs in real time, like tail f. Journoctl F. Journoctl FU Engine X service. View logs for a specific time period. Journoctl since 2023 to 1-1-10.00 until 2023 to 1-1-10.50. Journoctl since yesterday. View kernel messages. Journoctl K. Traditional log files /var/log. While Journoctl is primary, many services still write to plain text files in var/log. Knowing which files to check is essential. var/log/syslog, Ubuntu/Debian, general system activity, including boot messages, authentication, and various service logs. var/log/messages, RHEL sent OS, similar to syslog. var/log/authlog, authentication logs, including sudo attempts, SSH logins. var/log/kernlog, kernel messages and warnings. var/log/dpkglog, package installation removal logs. Web server logs, e.g., Apache, Nginx, typically in /var/log/ Apache 2/ or /var/log/nginx/ for access and error logs. Database logs, location varies, often within /var/log/mysql/ or var/log/postgresql/. You can use cat, less, grep, and tailf, as discussed in Chapter 3, to inspect these files. 12.3. Monitoring system resources. Performance issues often stem from resource bottlenecks. Here's how to check CPU, memory, and disk usage. CPU usage. top/htop. Reviewed in Chapter 8, these tools immediately show you processes consuming the most CPU. Look for processes taking consistently high CPU percentages. MPStat, multiprocessor statistics, provides a detailed breakdown of CPU utilization per CPU or core. Install with sudo apt install systat. MPStat1 #report CPU activity every 1 second. Memory usage. FreeH displays the amount of free and used memory, RAM, and swap space in human-readable format. FreeH. Look at the total, used, and available columns. Available is actual usable memory. If available is consistently low, your system might be swapping to disk, which significantly slows things down. Top/htop also show memory usage per process. Sort by MEM% to see which processes are consuming the most memory. Disk usage. DFH, disk file system, reports disk space usage for mounted file systems in human-readable format. This helps identify if a partition is critically full. DFH. Pay attention to the use percent column. A high percentage, e.g., 80 to 90% on your root/or home partition can cause instability. Do/sh path to directory, disk usage, summarizes disk usage of a specific directory, useful for finding large files or folders. Do/sh, cache pip hash check size of pip cache. Do/sh for /log hash check size of log directory. To find the largest files in a directory, find path to directory type fexec do/h, plus sort rh head n10. I/O input-output performance. Heavy disk I/O can be a bottleneck, especially for databases or large file operations. Iostat I/O statistics provides device utilization, queue lengths, transaction rates, and statistics for I/O devices. Install with sudo apt install systat. Iostat x1 hash extended statistics every 1 second. Look at the %util, percentage of time the device is busy, and await average I/O wait time columns. 12.4 Network Troubleshooting Recap from Chapter 9. Networking issues are common, especially for applications relying on external services. Ping google.com/ping8.8.8.8. Check basic internet connectivity and DNS resolution. IP check your local IP address and network interface status. IP route, verify your routing table and default gateway. Dig google.com or nslookup. More detailed DNS lookup. Install dnsutils if dig is not found. sstomp, check listening ports to ensure your application or service is actually listening on the expected port. curl http localhost, port or curl http//yourserverip, port, test if your local web service is reachable. Sudo ufwa status, check firewall rules. 12.5 Common developer troubleshooting scenarios. 1. My application won't start. Check its logs, journoctl for services or tail F for a file log. Permissions. Is the script executable marked as executable, chmod +x? Does it have read-write access to necessary files directories? Dependencies. Are all required libraries installed? Often seen as module not found error in Python or cannot find module in Node.js. Configuration. Is your config file correct? E.g., database connection strings, API keys, port in use. Check sstomp to see if another process is already listening on the port your application needs. 2. My application is slow. Top/htop. Is your application consuming excessive CPU or memory? Free h. Is the system low on RAM, causing excessive swapping? Iostat. Is there high disk I/O, indicating a bottleneck with disk reads-writes, e.g. database? Network. Is your application waiting on a slow external API? Use ping to external services or check curl response times. 3. My disk is full. DFH. Identify which partition is full. Sudo do/sh. Recursively check top-level directories for large usage. Drill down into the largest ones. Often, /var/log old logs, /var/cache/apt/package cache, or ~downloads are culprits. Temporary files in /tmp or large Git repositories can also grow. 4. I can't connect to my database service. Is it running? Sudo systemctl status MariaDB or PostgreSQL Redis Docker. Is it listening on the right interface port? sstomp grep SQL or the relevant port. Check if it's only listening on 127.0.0.1 localhost when you need to access it from another machine or Docker container. Firewall. Is the port open? Sudo ufwa status. Credentials network config. Asterisk is your application using the correct username, password, hostname, and port for the database. 12.6 Using strace for deeper debugging. For really stubborn issues where an application is crashing or behaving unexpectedly, strace is an advanced tool that traces the system calls made by a process. This can reveal what files it's trying to access, what network connections it's attempting to make, or what errors it's receiving from the kernel. Strace, Miprable Matacap. Strace, PPID hash attached to a running process. Strace output can be very verbose, but looking for EACCES, permission denied, ENOENT, no such file or directory, or other ERRNO values can be highly insightful. Effective troubleshooting is a skill honed through practice. The more you apply these tools, the faster you'll become at identifying and resolving issues in your Linux development environment. Remember to keep a systematic approach and use the vast resources of the Linux community and internet forums when you get stuck. In the next chapter, we'll shift our focus to security, how to protect your Linux development machine and its data. 13. Linux security best practices for developers. Security is paramount in today's interconnected world, and your development machine is no exception. As a developer, you're often handling sensitive intellectual property, API keys, database credentials, and potentially interacting with production systems. A compromised development machine isn't just an inconvenience. It can be a gateway for attackers to gain access to your projects, your company's infrastructure, or even your client's data. This chapter outlines essential security best practices for developers working on Linux. While comprehensive system security is a vast field, focusing on these fundamentals will significantly reduce your attack surface and protect your work. 13.1 Principle of Least Privilege. This is a core security principle. Grant users and processes only the minimum permissions necessary to perform their required tasks. Avoid running as root. As discussed in previous chapters, never use the root account for daily development work. Always use a regular user account and only use sudo when specifically required for administrative tasks. This limits the potential damage if your account is compromised or if you accidentally execute a harmful command. Restrict file permissions. Regularly review permissions on your project files, configuration files, and private keys. Private keys, SSH, GPG, API keys, should ideally have 600 RW permissions, meaning only the owner can read-write. Sensitive configuration directories should be 700 RWX. When collaborating, ensure shared files or directories have appropriate group permissions, not world-writable O+W. Recall chmod from Chapter 4. 13.2 Keep your system updated. Outdated software is often vulnerable. Exploits target known weaknesses in older versions of operating systems, applications, and libraries. Regular system updates. Make it a habit to regularly run system updates. For Ubuntu/Debian, sudo apt update and sudo apt upgrade. Consider running this weekly or at least monthly. Don't indefinitely postpone reboots if updates require them, as critical kernel and security patches often do. Application updates. Keep your development tools, IDEs, programming language runtimes, and libraries updated. Use your package manager, apt, for system-installed software. For language-specific packages, e.g., npm for Node.js, pip for Python, ensure your project dependencies are also kept reasonably current. 13.3 Secure Remote Access, SSH. SSH, Secure Shell, is the primary way to connect to remote Linux servers, but it must be secured. Use SSH key authentication. Disable password authentication for SSH on your servers. Instead, use SSH key pairs. Your public key is placed on the server, and your private key, kept secret and secure on your local machine, authenticates you. Generate an SSH key pair, if you don't have one. SSH keygen, TED 25519C, your email at example.com. Follow the prompts. It's highly recommended to set a strong passphrase for your private key. Protect your private key. Ensure your private key file, // SSH/IDID 25519 by default has 600 permissions. chmod 600 // SSH/IDID 25519. Use SSH agent. For convenience, use SSH agent to store your unlocked private key in memory, so you don't have to type your passphrase every time you connect. Eval SSH agent s, start the agent. SSH add // SSH/IDID 25519 add your key, you'll be prompted for passphrase. Disable root login on servers. Prevent direct root logins via SSH. Force users to log in as a regular user and then use sudo for administrative tasks. 13.4 Manage your firewall. A properly configured firewall is your system's first line of defense against unwanted network connections. Enable UFWA. Uncomplicated firewall is the default choice for Ubuntu and makes firewall management simple. Ensure it's active. Sudo UFWA enable. Configure it to deny all incoming connections by default and only explicitly allow what's needed. For SSH access, always allow port 22 before enabling the firewall, or you could lock yourself out. Example: sudo UFWA allow SSH hash allow SSH, port 22. Sudo UFWA allow HTTP hash allow HTTP, port 80. Sudo UFWA allow HTTPS hash allow HTTPS, port 443. Hash only allow specific necessary ports for dev work, e.g., sudo UFWA allow 3000/TCP hash if your dev server runs on 3000. Sudo UFWA enable. Sudo UFWA status verbose. Close unused ports. Regularly check open ports using sudo sstalp from Chapter 9 and ensure only necessary services are listening. 13.5 Manage sensitive data. Developers often deal with API keys, database credentials, and other secrets. Never hardcode these directly into your source code. Environment variables. Use environment variables to store secrets. Your application can read these at runtime. Export database URL equals postgresql//user, password at host, port/db. Hash when running your app, hash python myapy. Env files. For local development, env files e.g., using Python doten for Python or doten for Node.js are common. These files are typically added to gitignore, see Chapter 10, so they are never committed to version control. Secret management tools. For more advanced scenarios and production, consider using dedicated secret management tools, e.g., HashiCorp Vault, AWS Secrets Manager, Google Cloud Secret Manager. 13.6 Be wary of unknown software and sources. Only install from trusted sources. Stick to your distribution's official package repositories for software apt. For third-party software, use official PPAs with caution or download directly from reputable vendors. Be skeptical of random scripts or binaries found online. Verify signatures. When downloading software not from a package manager, if available, verify its cryptographic signature to ensure it hasn't been tampered with. Inspect scripts. Before running any script downloaded from the internet, e.g., curl bash, always inspect its contents, curl less or download, review, then execute. A single malicious line can compromise your system. 13.7 Use strong, unique passwords and multi-factor authentication. Strong passwords. Use long, complex passwords for your user accounts, especially if you have pseudo privileges. Mix uppercase and lowercase letters, numbers, and symbols. Password manager. Use a reputable password manager, e.g., Bitwarden, KeePassXC, to generate and store unique, strong passwords for all your online accounts and local services. Multi-factor authentication, MFA. Enable MFA wherever possible: email, social media, code repositories, cloud providers. This adds an extra layer of security, usually requiring a code from your phone in addition to your password. 13.8 Backups. While not strictly security in the sense of keeping intruders out, regular backups are crucial for data recovery in case of system failure, accidental deletion, or in a worst-case scenario, a ransomware attack. Automate backups. Use tools like rsync for local network backups or cloud backup services for your critical project data and configuration files. Offsite/cloud backups. Store backups in a separate location, ideally offsite or in a cloud storage provider. Test backups. Periodically test your backup restoration process to ensure your backups are viable. 13.9 Use a virtual private network, VPN, on public Wi-Fi. When connecting to public Wi-Fi networks, coffee shops, airports, sensitive data can be intercepted. A VPN encrypts your internet traffic, providing a secure tunnel. 13.10 Antivirus malware scanners, optional for Linux. Linux is generally less susceptible to malware than Windows, primarily due to its robust permission model, smaller market share, making it less of a target for mass exploits, and the open-source nature leading to quicker patch releases. Most Linux users don't run active antivirus. However, if you are regularly exchanging files with Windows users to avoid passing on Windows-specific malware, you are running a mail server or file server. Your company policy requires it. Then, tools like ClamAV can be installed. For a developer's workstation, diligent application of the above practices, updates, firewalls, strong passwords, trusted sources, usually provides more effective protection than an antivirus solution alone. Security is an ongoing process, not a one-time setup. By integrating these best practices into your daily workflow, you can significantly enhance the security posture of your Linux development environment and protect your valuable work. In our final chapter, we'll look at next steps for continuing your Linux journey, exploring advanced topics and the supportive Linux community. 14. Next steps, advanced topics and community. Congratulations! You've reached the end of the Developer's Linux Playbook. If you've followed along, you've not only set up a Linux development environment, but also gained a practical understanding of its core components, mastered essential command line tools, learned to manage software, debug issues, and apply fundamental security practices. You're no longer just using Linux, you're leveraging its power as a true development hub. However, the world of Linux is vast and ever-evolving. This book has served as your foundational guide, opening doors to a universe of possibilities. This final chapter will point you towards advanced topics to continue your learning journey and highlight the incredible community that supports the Linux ecosystem. 14.1. Continuing your Linux journey. Advanced topics. The skills you've acquired are solid building blocks. Here are some areas where you can deepen your expertise. 14.1.1. Advanced shell scripting and automation. While we introduce the basics, shell scripting can be incredibly complex and powerful. Regular expressions, regex. Master regex for powerful text searching and manipulation with tools like grep, sed, and awk. Advanced control flow. Explore case statements, select loops and error handling, set trap, functions and libraries. Organize complex scripts into reusable functions and create your own script libraries. Debugging shell scripts. Learn to use set x for command tracing, set v for verbose output, and bash n for syntax checking. Cron jobs. Automate running your scripts at specific times or intervals using cron. Tooling around the shell. Explore tools like tmux or screen for persistent terminal sessions, and zsh or fish as alternative shells with more features than bash. 14.1.2. Advanced text editing, vim/emacs. If you chose to use Nano for simplicity, reconsider diving deeper into Vim or exploring Emacs. Vim/NeoVim. Explore advanced Vim concepts like macros, registers, custom key mappings, and more deeply integrate language servers, LSB, for an IDE-like experience directly in your terminal. Learning a Vim tutor is a great next step. Emacs, another powerful, extensible, customizable, and programmable text editor known for its Lisp-based extensibility. Emacs users often call it an operating system within an operating system due to its vast capabilities beyond just text editing. 14.1.3 Deeper dive into Docker and containerization. The container ecosystem is booming. Docker networking. Understand how Docker containers communicate with each other and with the host system using various networking drivers. Docker volumes. Master persistent data storage for containers. Multi-stage builds. Optimize Docker images for size and efficiency. Container registries. Learn to push and pull your own custom images from Docker Hub or private registries. Kubernetes. For deploying and managing containerized applications at scale, Kubernetes is the de facto standard. It has a steep learning curve, but is essential for modern DevOps and cloud-native development. Look into Minikube or K3s for local Kubernetes clusters. 14.1.4 Virtualization and Cloud Computing. libvirt/kvm. If you're running VMS on a Linux host, explore KVM and libvirt for more performant and integrated virtualization. Vagrant. Continue using Vagrant for consistent and reproducible VM-based development environments. Cloud Provider Linux VMS. Get hands-on experience provisioning and managing Linux virtual machines on major cloud platforms like AWS EC2, Google Cloud Compute Engine, or Azure Virtual Machines. 14.1.5 Linux System, Administration and Networking. For developers who also manage servers, deeper sysadmin skills are invaluable. SE Linux/App Armor. Understand these mandatory access control systems for enhanced security. File System Management. Explore different Linux file systems, XFS, ZFS, BTRFS, partitioning schemes, logical volume management, LVM. Network configuration. Learn to configure advanced network setups, including static IP addresses, bonding interfaces, and setting up VPN client servers. Monitoring tools. Delve into more advanced monitoring tools like Grafana, Prometheus, Nagios, or Zabbix for real-time system and application monitoring. 14.1.6 Kernel and low-level programming. For the truly curious, diving into the Linux kernel or low-level programming in C/C++ offers a comprehensive understanding of how everything works under the hood. This can lead to embedded systems development, device drivers, or performance optimization. 14.2 The Linux Community, your greatest resource. One of Linux's biggest strengths is its vibrant, open, and incredibly helpful community. When you encounter a problem or want to learn something new, you're rarely alone. Online forums and communities. Ask Ubuntu/Unix and Linux Stack Exchange. Excellent resources for specific questions and problems. Reddit. Subreddits like rLinux, rLinux for Noobs, r/Linux Questions, r/Commandline, r/sysadmin, rvim, rdocker are active and supportive. Official distribution forums. Most distributions have official forums, e.g. Ubuntu forums. Documentation. Man pages. Never underestimate the man command. It's the most authoritative source of information for most commands. Arch Linux Wiki. Even if you don't use Arch, its wiki is an incredibly detailed and well-maintained resource for almost any Linux topic. Official project documentation. Always check the official documentation for specific software or libraries you're using. Open source projects. Contribute to open source projects. It's a fantastic way to learn, improve your coding skills, and interact with experienced developers. Start small, perhaps by fixing a typo in documentation or submitting a minor bug fix. Local Linux user groups, LUGS. Check if there's a Linux user group in your area. They often hold meetings, workshops, and provide a great opportunity to connect with other enthusiasts. 14.3 Final thoughts. Linux is more than just an operating system. It's a philosophy of openness, collaboration, and control. By embracing Linux, you've chosen a path that offers unparalleled flexibility, power, and a deep understanding of the computing landscape. Your journey is just beginning. Keep experimenting, keep breaking things, in a safe environment, of course, and keep learning. The skills you acquire and the insights you gain from working with Linux will not only make you a more capable and efficient developer, but will also broaden your understanding of technology in profound ways. Happy hacking!